The universe presents itself to our eyes as a canvas of glittering lights spread across an infinite darkness, yet what we call darkness is not truly empty. Beyond the reach of telescopes, and beyond the comforting glow of stars, there exist entities that devour light itself. These are black holes, the most enigmatic and terrifying phenomena in all of physics. They are born in silence, cloaked in shadows, and revealed only by the violence they unleash on the space around them. To understand why they are so feared and yet so captivating, we must imagine a region where gravity has grown stronger than any force we know, where nothing, not even light, can resist its pull. A black hole is not a tangible object that one can touch or hold. It is not a planet nor a star in the usual sense. It is instead a region of space-time where the rules we take for granted break down. At its edge lies the event horizon, a boundary so absolute that once crossed, there is no possible return. For a traveler, it would appear as a veil, a line painted on the universe, and passing it would mean vanishing from the rest of existence forever. Outside observers would never truly see this final step, as the last flashes of light from the traveler would appear to freeze at the horizon. But from the traveler's own perspective, the crossing would occur in finite time, quick and irreversible. The concept of the event horizon is both simple and incomprehensible. Imagine throwing a ball into the air on Earth. If you throw it too gently, it falls back down. Throw it harder, it rises higher before returning. Throw it at just the right speed, and it escapes Earth entirely. That speed is called escape velocity. For a black hole, the escape velocity at the horizon equals the speed of light, the ultimate cosmic speed limit. Since nothing can move faster than light, no particle, no signal, and no information can ever escape. From outside, the interior is sealed forever, and whatever story unfolds within is hidden beyond a curtain of perfect darkness. Yet even this is not the full horror. At the core of the black hole, behind the horizon, lies the singularity. It is not a physical ball or point that can be visited. It is instead the breakdown of space-time itself, a place where gravity crushes matter into infinite density and the laws of physics as we know them cease to function. Our equations collapse into infinities. Time and space themselves fold into something unrecognizable. The singularity is the ultimate cliff in science, where knowledge fails and speculation begins. To speak of it is to step beyond certainty into mystery. The presence of black holes in the universe is not merely theoretical. They are real, and their fingerprints can be seen in the violent dances of matter around them. Gas pulled into their grasp heats up and glows with deadly radiation. Stars wandering too close are stretched and torn apart, their remnants spiraling inward in a luminous scream. From a distance, this destruction lights up galaxies, but the devourer at the center remains unseen, silent, and endlessly hungry. The paradox of black holes is that their invisibility makes them all the more terrifying, for they reveal themselves not directly, but by the suffering they inflict on their cosmic surroundings. Why do these monsters inspire such dread? Part of it is the primal fear of being swallowed, of being consumed utterly with no possibility of return. Yet another part is fascination. Black holes are not only destroyers, but also gateways to deeper truths. They embody Einstein's theory of general relativity pushed to its breaking point. They challenge us with puzzles that link gravity, quantum mechanics, and the very structure of space-time. To study them is to confront the limits of human understanding. They also inspire a strange awe because of their dual nature. They are killers and creators at once. By consuming matter, they shape galaxies. By colliding, they shake the fabric of the universe itself, sending ripples of gravitational waves across billions of light years. Without them, the universe would not be the same. They are not mistakes in creation, but engines of cosmic evolution, sculptors working invisibly in the dark. Imagine floating in the void, far from any star, with nothing but silence around you. Then imagine approaching a black hole. From a safe distance, you would see stars twisted into arcs of light as gravity bends them around the darkness. The black hole would not appear as a simple hole, but as a sphere of perfect black surrounded by a distorted halo, a visual echo of the universe itself. Step closer, and time itself would begin to stretch. Seconds for you could become centuries for others. Closer still, and the pull becomes irresistible, a fall that accelerates beyond comprehension, until the event horizon swallows you without sound. To witness this is to encounter the closest thing to infinity within nature. And yet, despite their terror, black holes are everywhere. Our own galaxy, the Milky Way, is believed to contain hundreds of millions of them. They lurk in binary star systems, hiding until they awaken to feed. They dominate the centers of galaxies as supermassive engines. Some drift invisibly through interstellar space, rogue predators waiting in silence. Each is unique in its history, but all share the same fate: to grow by devouring, to rule in silence, and to leave mysteries behind. From the ashes of stars, from the collapse of giants, from the hidden corners of space, black holes are born. Some are small, the remains of stellar deaths. Others are titanic, billions of times heavier than our sun. From these different scales arise the full spectrum of black hole horrors. To begin our journey into this cosmic underworld, we must start with the most common kind, the killers that form when stars themselves fall into their own gravity. From these stellar remnants to the most monstrous giants ever known, let us now step deeper into the dark and meet the most terrifying black holes in existence. The universe is often described as vast and silent, but when we look closer at the story of black holes, we discover it is neither quiet nor gentle. These cosmic entities are not rare curiosities tucked away in distant galaxies. They are common children of the stars, born when massive suns reach the end of their lives. A star spends millions to billions of years fusing hydrogen into helium, burning with a steady glow. But when its fuel is exhausted, when its balance between outward radiation and inward gravity collapses, the star can no longer support its own weight. In that moment, a cosmic catastrophe unfolds. The core contracts, the outer layers explode outward in a supernova, and what remains is a remnant so dense that not even light can escape. That is how the first black holes come into being. This process is more than violent. It is the very definition of finality. Imagine a star many times the mass of our sun. For most of its life, it appears stable, its radiation and heat radiating into space, yet deep inside, its core is engaged in a desperate struggle. When fusion can no longer resist gravity, collapse becomes unstoppable. The entire mass implodes in seconds. For the outer layers, the explosion is their release, spreading elements across the galaxy. For the core, the implosion continues until the singularity is born. The result is a stellar mass black hole, usually ranging from a few to dozens of times the mass of our sun. Though small compared to their supermassive cousins, these stellar remnants are among the most terrifying. They are the unseen companions in binary star systems, waiting silently for their partner to wander too close. Once matter begins to fall toward them, it forms an accretion disk, spiraling inward at nearly the speed of light. Friction heats the gas to millions of degrees, releasing X-rays that can be detected across interstellar distances. These signals were the first clues that black holes were not mere theoretical constructs, but real predators lurking in the night sky. the discovery of Cygnus X1 was the moment astronomers realized they had truly found one. But before we move to such examples, let us dwell on the nature of their gravity. A stellar mass black hole can be only a few kilometers across, yet its pull is so absolute that even light cannot break free. Imagine compressing a star like our Sun into a sphere the size of a city. Every photon emitted from its surface would curve back into its center. For an object or person drifting nearby, the consequences would be unimaginably gruesome. The difference in gravity between the head and the feet, known as tidal forces, would stretch the body apart in a process sometimes called spaghettification. Bones, organs, even molecules would be stretched into long, thin strands drawn into the abyss. It is not death by fire or collision, but by the fundamental tearing of space-time itself. Even more haunting is the way time behaves near these objects. To an observer falling toward the event horizon, time ticks normally. Seconds follow seconds. But to someone watching from a safe distance, the falling observer appears to slow down, to freeze on the brink of the horizon, never truly crossing. From the outside, they seem suspended forever, their final moments stretched into eternity. This paradox arises because gravity warps time as well as space. Near a black hole, time itself bends, slowing as the pull of gravity deepens. The black hole does not just trap matter and light, it traps time. And yet, despite the violence of their births and the horror of their pull, black holes are profoundly important to the cosmos. When a massive star dies in a supernova, it does more than create a black hole. It seeds the galaxy with elements necessary for life, including carbon, oxygen, and iron. Without this process, planets like Earth would never have formed, and life itself would never have emerged. Black holes are therefore both destroyers and creators, forces of ending and beginning entwined. The very atoms in our bodies were forged in the violent deaths of stars that may have given rise to black holes long ago. In this sense, we are intimately connected to them, born from their shadow as much as from their light. This duality makes them more than just monsters. They are also teachers. By studying their effects on nearby stars, astronomers learned to detect them indirectly. By measuring the X-rays from their accretion disks, scientists mapped their feeding habits. By observing how stars orbit unseen companions, researchers identified the hidden masses that revealed their presence. Each discovery deepened both fear and fascination. The more we learned, the more mysterious they became. How could something that bends space-time like a sheet of paper exist? How can infinities be part of nature? Black holes also invite us to explore the unknown edges of physics. At the singularity, our equations of general relativity, so successful in describing gravity on cosmic scales, collapse into nonsense. Quantum mechanics, which rules the world of particles, also fails to describe what happens. Somewhere between these two great theories lies the true description of reality. Black holes are not just astronomical oddities. They are clues to the deepest questions in science. What is the nature of time? Can information be destroyed? Is space-time itself continuous or discrete? Every question is sharpened by the shadow of the black hole. Imagine civilizations elsewhere in the galaxy watching the same dark giants, wondering the same things. Perhaps they too fear the invisible predators that might drift unseen between stars. Perhaps they too have pointed instruments skyward, capturing the X-ray screams of matter being devoured. Across the universe, the terror and fascination of black holes is universal. They are not confined to our imagination alone, but are written into the very fabric of the cosmos. As our understanding grew, so did the realization of scale. Stellar mass black holes are terrifying, yes, but they are only the beginning. If such killers can be born from a single star's death, What happens when entire swarms of them merge? What monsters lurk at the hearts of galaxies, where millions or billions of suns' worth of matter has collapsed into a single gravitational abyss? The thought stretches the imagination to its limit. From these beginnings, we prepare to step into the realm of the Titans, the black holes whose scale dwarfs the human mind. The first step in this journey, however, is to look closely at the stellar mass black holes themselves. They are not exotic rarities, but common children of stellar death. They are scattered across the Milky Way in numbers beyond counting, some revealed, others hidden in silence. They are the most numerous killers in the cosmic night, the everyday predators of the galaxy. And from them, larger horrors grow. Part of the dread that black holes inspire comes from how they force us to think about what it means to exist. A planet orbiting a star can be measured, mapped, and touched in thought. A star can be studied in its cycles of fusion and light. But a black hole resists every attempt at simple description. It is not a place where matter resides. It is a boundary and a silence. When we speak of an event horizon, we are speaking of a surface that has no surface, a sphere made only of absence. Behind it is not space as we know it, but a region from which no traveler, no signal, and no truth can return. The very existence of black holes shows that nature does not respect the limits of human imagination. When Albert Einstein first wrote the equations of general relativity, he himself doubted that such extreme solutions could exist. Yet the math was clear. When enough mass is compressed into a small enough volume, space-time curves so steeply that escape becomes impossible. At first, these were seen as curiosities, strange implications buried deep in theory. But the universe is under no obligation to fit our expectations. Soon, astronomers found evidence of stars orbiting invisible companions, X-ray sources flaring in the heavens, and violent outbursts of energy that could be explained only by black holes. What once seemed unthinkable became undeniable. And still, even with evidence in hand, the terror remains. For unlike other cosmic wonders, black holes can be near without being noticed. They do not shine. They do not announce themselves unless feeding. A stellar mass black hole could be drifting in our galactic neighborhood, invisible against the black. Unless it passed close enough to bend starlight or disturb orbits, it would remain hidden. This possibility makes them not only awe-inspiring, but also chilling. We may share our galaxy with countless unseen monsters, waiting silently, neither friend nor foe, simply following the dictates of gravity. For those who try to imagine falling into such an object, the mind stumbles. Spaghettification may sound like a curious metaphor, yet it describes the inexorable truth of tidal gravity. As one falls feet first toward a black hole, the pull on the feet grows far stronger than the pull on the head. The body stretches, nerves fire in agony, molecules themselves elongate until no recognizable form remains. To an outside observer, the falling figure freezes at the horizon, locked in a final instant that never ends. But from within, the journey continues without pause, a plunge into the singularity that no theory can yet fully describe. This duality between what is seen and what is experienced is part of the deep strangeness that makes black holes so terrifying. Yet it is worth pausing to remember that what horrifies us also guides us to deeper understanding. Black holes are not simply cosmic predators. They are laboratories where nature conducts experiments impossible anywhere else. By watching how matter behaves as it falls in, by measuring the arcs of stars caught in their grip, by detecting the waves they send through space-time when they collide, we are given a window into regimes of gravity, time, and energy that would otherwise remain hidden. Every discovery about black holes is a step toward a more complete picture of the universe itself. The most frightening aspect, perhaps, is that these monsters are not distant curiosities in some unreachable realm. They are part of our own galaxy, shaping it silently. At the very center of the Milky Way, 26,000 light-years from Earth, lies a supermassive black hole, millions of times the mass of the Sun. The stars near the galactic core dance around it in tight orbits, their paths betraying the invisible master in their midst. The fact that our own cosmic home is bound together by such a dark engine is both terrifying and profound. We live in a galaxy that thrives around a singularity, a cosmic predator that has silently ruled since its birth. This reality forces us to reconsider fear. Are black holes merely destroyers, or are they essential pillars of creation? Without them, galaxies might not form in the same way. Without them, stars might not be arranged into the structures we see. Even life itself may owe its existence indirectly to the role black holes play in shaping the cosmos. In this sense, they are both terrifying and necessary. They are not intrusions into the story of the universe. They are central characters. As we look outward, we find that the story does not end with stellar black holes alone. These smaller killers born from collapsing stars are only the beginning. They populate the night in uncountable numbers, the common assassins of the cosmos. But beyond them rise even greater terrors. There are black holes so large they can swallow entire solar systems, so powerful they can outshine galaxies, and so ancient they may date back to the dawn of time itself. From the most modest stellar remnants to the true titans of creation, the spectrum of black holes stretches across scales that defy comprehension. Our journey into this realm of cosmic darkness has only begun. We have stepped into the shadows and touched the edge of the event horizon. We have glimpsed the singularity as an abyss where science falters. And we have felt the awe and dread of knowing that such monsters exist, not only in the far reaches of the universe, but also in our own galactic neighborhood. Yet the story is far from finished. From here, we will descend into the next layer of the abyss, where stellar mass black holes reveal themselves as the common killers of the cosmos, hidden in plain sight yet capable of extraordinary destruction. To know them is to take the first step toward understanding the full scale of terror and wonder that black holes bring to the universe. The birth of a stellar mass black hole is one of the most violent transformations in the cosmos. It begins with a star that has lived for millions of years, quietly fusing hydrogen into helium, balancing its immense gravity with the outward pressure of radiation. For a time, this balance holds, a delicate truce between collapse and expansion. But no star lives forever. When the fuel runs out, gravity claims victory. The outer layers explode outward in a supernova that can outshine entire galaxies for a brief moment, while the core implodes in silence. What remains is a corpse so dense that space and time bow inward around it. This is the birth cry of a stellar mass black hole, the most common predator in the galactic wilderness. These killers are small in cosmic terms. A typical stellar mass black hole weighs perhaps 5, 10, or 20 times the mass of the Sun, yet compresses this weight into a sphere no larger than a city. The scale is difficult to grasp. Imagine shrinking the Sun, a ball of burning plasma nearly 1.5 million kilometers across, into an object only a few kilometers wide. The gravitational pull of such a remnant is beyond comprehension. Once created, it is permanent, for nothing can push against its collapse. The black hole endures, patient and silent, until a victim strays too close. And yet, despite their silence, these stellar killers are not hidden from science. They reveal themselves in indirect ways, through the violence they inflict on their surroundings. When they are paired with another star, the story becomes particularly grim. Gas is pulled from the companion, spiraling inward to form an accretion disk. The friction of this whirlpool heats the gas to millions of degrees, releasing X-rays that pierce the darkness. It is through these signals that astronomers first confirmed the existence of black holes. They were not imagined predators, but real forces lurking in our sky. The first true candidate discovered was Cygnus X1, a stellar mass black hole in the constellation of the Swan. Detected in the 1960s through its powerful X-ray emissions, it marked the beginning of black hole astronomy. Here was a star orbiting an invisible companion more massive than any neutron star could be. Only a black hole could explain the observations. For the first time, humanity had evidence that these monsters were not theoretical ghosts, but genuine features of the universe. Cygnus X1 became a symbol, a confirmation that black holes haunted the Milky Way. Another infamous example is V404 Cygni, also located in the Swan constellation. This stellar mass black hole lies around 8,000 light-years away and has erupted multiple times in spectacular outbursts. During one such flare, it became one of the brightest X-ray sources in the sky, visible even to amateur astronomers through small telescopes. Such outbursts occur when matter from its companion star piles into the accretion disk and then plunges inward all at once, releasing unimaginable amounts of energy. These episodes remind us that black holes, though invisible themselves, can suddenly announce their presence with cosmic violence. Part of the horror of stellar mass black holes is their sheer abundance. Astronomers estimate that our galaxy alone may host hundreds of millions of them, the remnants of generations of massive stars that lived and died long before humanity emerged. Most drift silently through space, unlit and undetected. They are the quiet predators of the galaxy, waiting for chance encounters with gas clouds or wandering stars. Any one of them could pass within light years of Earth without notice, invisible save for the subtle warping of starlight. The fact that they are so common and so hidden only deepens their menace. Their destructive power is not limited to the stars they consume. When a stellar mass black hole devours too much material at once, it can unleash jets of energy that blast outward across light years. These jets, moving at nearly the speed of light, can sterilize entire regions of space, stripping planets of atmospheres and halting the formation of new stars. In this way, even the smallest black holes can influence the evolution of galaxies, carving scars across the cosmic landscape. To fall into such an object is to meet an end more final than death. Near the horizon, the pull becomes irresistible. Tidal forces tear bodies apart, stretching them into strands thinner than atoms. Time dilates, slowing to a crawl as the victim is frozen on the brink, a ghostly image for eternity. Inside, the singularity waits, a place where even the idea of existence may lose meaning. These horrors are not fantasy, but consequences of physics itself, written in the equations that describe gravity and motion. Stellar mass black holes are therefore both ordinary and extraordinary. They are the inevitable outcome of massive stars, scattered across the galaxy in numbers that defy counting. Yet each one is a window into the most extreme conditions the universe can produce. They are killers, yes, but also teachers, showing us the limits of matter and the bending of time. Their very existence challenges us to confront a universe stranger and darker than any myth. And still, these are but the smallest of the monsters. They are the foot soldiers of darkness, countless and deadly, but beyond them lie creatures of greater scale. Between the stellar killers and the giants at galactic centers exists a rare and mysterious class, a bridge between worlds. These intermediate mass black holes are elusive, their existence debated, their nature uncertain. They may hold the secrets of how the largest black holes came to be. From the familiar horrors of stellar mass killers, we now move toward the shadows of the missing link, the intermediate black holes that may reveal the hidden evolution of cosmic predators. These stellar killers, though relatively small compared to the giants at galactic centers, display a diversity that makes them endlessly fascinating and terrifying. Not every stellar mass black hole is born the same way. The fate of a star depends on its mass, its composition, and its environment. Some stars collapse directly into black holes without a visible supernova, vanishing quietly into darkness. Others explode in cataclysms so bright that they outshine their host galaxies before leaving behind the compact remnant. In both cases, the end result is the same: a region of space-time cut off from the rest of the universe, a gravitational predator lying in wait. One of the unsettling truths about these objects is how close they can be. While supermassive black holes lie at the hearts of galaxies, stellar mass black holes can lurk almost anywhere. They can be found in binary systems within a few thousand light-years of Earth, practically in our cosmic backyard. For example, the system known as a 0620-00, located in the constellation of the Unicorn, is home to a stellar mass black hole only a few times heavier than the Sun. It flares periodically as it devours matter from its companion star, lighting up the night sky with bursts of X-rays. The idea that such predators exist so near to us reminds us that the universe is not a tranquil place, but a landscape shaped by violence. Another chilling example is V404 Cygni, already notorious for its outbursts. In 2015, it erupted in a series of violent flares that astonished astronomers. The brightness of the system increased by a factor of hundreds in mere hours, a testament to the chaotic feeding frenzy taking place as the black hole consumed its star. Observations revealed jets of material being blasted outward at near light speed, a demonstration that even small black holes can unleash power beyond human comprehension. The unpredictability of such events shows that black holes are not steady machines but unstable engines capable of sudden bursts of destruction. Beyond individual systems, the sheer population of stellar mass black holes is staggering. If hundreds of millions exist in the Milky Way alone, then billions must populate the universe. Most of them are dark, inactive, and invisible, detectable only when their gravity betrays their presence. Future surveys may reveal many more, but for now, we are left to imagine the unseen hordes drifting through space. They are the ghosts of dead stars, their legacies reduced to gravitational traps scattered across the cosmos. The thought that our galaxy is haunted by so many silent monsters is both thrilling and chilling. Yet despite their terrifying reputation, stellar mass black holes serve as cosmic laboratories. They allow scientists to test Einstein's theory of relativity in extreme conditions, observing the motions of companion stars, the warping of light, and the timing of X-ray flares provides evidence that space-time truly bends under immense gravity. Every observation confirms predictions made a century ago, yet each discovery also raises new questions. Do black holes truly destroy information? Does the singularity really exist, or will quantum gravity reveal a hidden structure? These stellar remnants are not just killers, but clues to the deepest mysteries of physics. What makes them even more intriguing is their potential to grow. When two stellar mass black holes encounter each other, they can form a binary pair, orbiting one another in a deadly dance. Over time, they spiral inward, releasing energy as gravitational waves. Eventually, they merge into a larger black hole, releasing a burst of power that can briefly outshine the entire visible universe in gravitational energy. Such mergers are no longer theory. In 2015, the LIGO Observatory detected the first gravitational waves, ripples in space-time, created by the collision of two stellar mass black holes. This discovery confirmed not only their existence, but also their role as dynamic, evolving entities that reshape themselves through violent unions. The detection of gravitational waves opened a new era of astronomy. For the first time, humanity could listen to the universe, hearing the faint echoes of black holes colliding billions of light years away. These signals revealed populations of black holes heavier than expected, suggesting that stars far larger than our Sun had collapsed in the early universe to create them. Each detection told a story of stellar death, collapse, and rebirth as a black hole. These stories are still being uncovered, but they suggest that the life cycle of stars may be more varied and violent than previously imagined. Consider for a moment what these events mean. Two black holes, each perhaps 30 times the mass of the Sun, spiral toward one another for millions of years. In their final seconds, they orbit each other dozens of times per second, their horizons whipping through space at half the speed of light. When they merge, the resulting black hole swallows the last remnants of their individuality, and a burst of gravitational energy, equal to several suns, converted entirely into waves, shakes the cosmos. For us on Earth, the signal is faint, stretching detectors by less than the width of a proton, yet it carries the story of titanic monsters colliding in silence. Stellar mass black holes are thus far more than the silent killers of binary systems. They are participants in cosmic symphonies of destruction and creation. They devour stars, unleash jets, and collide in bursts of space-time ripples. They are the most numerous black holes we know, and their behaviors continue to surprise us. Each observation is a reminder that the universe is alive with violence, that the night sky is a stage upon which invisible players act out dramas of unimaginable scale. And still, as terrifying as they are, they pale in comparison to what comes next. Beyond the realm of stellar mass, black holes lies a more elusive class, a possible bridge between the small killers and the titans at galactic centers. These intermediate mass black holes remain mysterious, rarely glimpsed and poorly understood. If they exist in large numbers, they may hold the secrets of how galaxies themselves were seeded. As we turn from the common killers to the missing links, the shadows deepen, and the mysteries grow even greater. Though we now recognize stellar mass black holes as common, their familiarity does not diminish their power to unsettle the imagination. They are the most approachable of cosmic monsters in scale, yet they remind us that death is an essential part of the universe's story. Every one of them marks the end of a star, an end so extreme that light itself is bound forever. When we look at the galaxy through this lens, we see a graveyard scattered with invisible tombs, each one a marker of violent collapse. But unlike ordinary tombs, these do not remain still. They continue to feed, to grow, and to influence their surroundings for billions of years. The process of feeding is not always steady. Many stellar black holes sip from their companions gently, allowing matter to stream steadily into their disks. But others gorge themselves suddenly, pulling in matter in great surges that release terrifying bursts of energy. These violent episodes can light up the sky and have been recorded as sudden, bright X-ray flares, lasting days or weeks. The drama of these outbursts speaks to the unpredictable nature of stellar black holes. They can wait silently for centuries, then roar to life in an instant, announcing their presence to any who watch the heavens. We also now understand that stellar mass black holes are more diverse in size than once imagined. While many weigh less than 20 times the mass of the Sun, some discovered by gravitational wave observatories are far heavier, approaching 50 or even 70 times solar mass. Their existence suggests that certain stars in low metal environments, stars born with fewer heavy elements, can collapse directly into heavier black holes without blowing themselves apart. This possibility opens a window into the early universe, when stars were massive, primitive, and capable of creating such remnants in large numbers. Each detection of a heavy stellar mass black hole tells us something new about the lives of the first stars and the violent cosmos in which they lived. The danger these objects pose is not confined to their feeding and flaring. Imagine a stellar black hole drifting unseen through space. Ejected from its birthplace by the kick of a supernova, it wanders the galaxy like a rogue predator, invisible except for its gravity. Should such an object pass through a dense region of gas or too near a star system, it could disrupt planetary orbits, strip atmospheres, or trigger collapses of material into its maw. The probability of one wandering into our solar system is small, but not zero. The thought alone is enough to remind us of how fragile our existence is in the wider cosmos. Even when they are not directly threatening us, stellar mass black holes are terrifying in concept. They turn the familiar physics of everyday life into something alien. Gravity, usually gentle and predictable, becomes absolute and crushing. Time, which we measure in steady beats of clocks, becomes distorted, stretched, and warped. Even information, the record of events, is questioned, for we do not yet know if the story of what falls into a black hole is lost forever or somehow preserved at the horizon. These puzzles strike at the core of what it means to know reality. Despite their horrors, there is beauty in how they shape the universe. By devouring stars, they release energy that can trigger new cycles of star formation. By colliding, they send ripples across space-time that we can now detect, giving us new senses to perceive the cosmos. They are participants in a grand cycle, endings that lead to beginnings, destructions that give way to creations. Without them, galaxies would evolve differently, and the cosmic story would lack its most dramatic chapters. Consider again Cygnus X1. When it was first identified, even Stephen Hawking placed a bet that it would not turn out to be a black hole. So skeptical was he that nature could create such extreme entities. Yet the evidence was undeniable. Decades later, Cygnus X1 remains a symbol of the moment when humanity crossed from theory into reality, from speculation into confirmation. It is more than a binary system. It is a reminder that black holes are not just thought experiments but neighbors, existing within the same galaxy we call home. V404 Cygni tells a similar story. Its eruptions have been watched by generations of astronomers, each event adding to the sense of awe and dread. It shows that even black holes only a few times the mass of the Sun can unleash energies comparable to entire stars. Every flare is a reminder that power in the universe is not always proportional to size. Sometimes, the smallest predators can strike with the greatest violence. Together, these systems illustrate the dual truth of stellar mass black holes. They are ordinary products of stellar death, yet extraordinary in the powers they wield. They are the silent background of the Milky Way, yet capable of shaking our understanding of physics when they collide or flare. They are killers, yes, but also guides pointing us toward deeper truths. And yet, for all their terror, they are not the ultimate black hole story. They are merely the foundation upon which greater mysteries rest. Between the stellar killers and the galactic titans lies a missing link, a category so elusive that only a handful of candidates exist. These intermediate mass black holes may bridge the gap between the common and the unimaginable, holding secrets about how supermassive black holes came into being. As we step beyond the realm of the common killers, we enter the shadows of speculation and rarity, where the next class of monsters waits to be revealed. The birth of a stellar mass black hole is one of the most violent transformations in the cosmos. It begins with a star that has lived for millions of years, quietly fusing hydrogen into helium, balancing its immense gravity with the outward pressure of radiation. For a time, this balance holds, a delicate truce between collapse and expansion. But no star lives forever. When the fuel runs out, gravity claims victory. The outer layers explode outward in a supernova that can outshine entire galaxies for a brief moment, while the core implodes in silence. What remains is a corpse so dense that space and time bow inward around it. This is the birth cry of a stellar mass black hole, the most common predator in the galactic wilderness. These killers are small in cosmic terms. A typical stellar mass black hole weighs perhaps 5, 10, or 20 times the mass of the Sun, yet compresses this weight into a sphere no larger than a city. The scale is difficult to grasp. Imagine shrinking the Sun, a ball of burning plasma nearly 1.5 million kilometers across, into an object only a few kilometers wide. The gravitational pull of such a remnant is beyond comprehension. Once created, it is permanent, for nothing can push against its collapse. The black hole endures, patient and silent, until a victim strays too close. And yet, despite their silence, these stellar killers are not hidden from science. They reveal themselves in indirect ways through the violence they inflict on their surroundings. When they are paired with another star, the story becomes particularly grim. Gas is pulled from the companion, spiraling inward to form an accretion disk. The friction of this whirlpool heats the gas to millions of degrees, releasing X-rays that pierce the darkness. It is through these signals that astronomers first confirmed the existence of black holes. They were not imagined predators, but real forces lurking in our sky. The first true candidate discovered was Cygnus X1, a stellar mass black hole in the constellation of the Swan. Detected in the 1960s through its powerful X-ray emissions, it marked the beginning of black hole astronomy. Here was a star orbiting an invisible companion more massive than any neutron star could be. Only a black hole could explain the observations. For the first time, humanity had evidence that these monsters were not theoretical ghosts, but genuine features of the universe. Cygnus X1 became a symbol, a confirmation that black holes haunted the Milky Way. Another infamous example is V404 Cygni, also located in the Swan constellation. This stellar mass black hole lies around 8,000 light-years away and has erupted multiple times in spectacular outbursts. During one such flare, it became one of the brightest X-ray sources in the sky, visible even to amateur astronomers through small telescopes. Such outbursts occur when matter from its companion star piles into the accretion disk and then plunges inward all at once, releasing unimaginable amounts of energy. These episodes remind us that black holes, though invisible themselves, can suddenly announce their presence with cosmic violence. Part of the horror of stellar mass black holes is their sheer abundance. Astronomers estimate that our galaxy alone may host hundreds of millions of them, the remnants of generations of massive stars that lived and died long before humanity emerged. Most drift silently through space, unlit and undetected. They are the quiet predators of the galaxy, waiting for chance encounters with gas clouds or wandering stars. Any one of them could pass within light years of Earth without notice, invisible save for the subtle warping of starlight. The fact that they are so common and so hidden only deepens their menace. Their destructive power is not limited to the stars they consume. When a stellar mass black hole devours too much material at once, it can unleash jets of energy that blast outward across light years. These jets, moving at nearly the speed of light, can sterilize entire regions of space, stripping planets of atmospheres and halting the formation of new stars. In this way, even the smallest black holes can influence the evolution of galaxies, carving scars across the cosmic landscape. To fall into such an object is to meet an end more final than death. Near the horizon, the pull becomes irresistible. Tidal forces tear bodies apart, stretching them into strands thinner than atoms. Time dilates, slowing to a crawl as the victim is frozen on the brink, a ghostly image for eternity. Inside, the singularity waits, a place where even the idea of existence may lose meaning. These horrors are not fantasy, but consequences of physics itself. written in the equations that describe gravity and motion. Stellar mass black holes are therefore both ordinary and extraordinary. They are the inevitable outcome of massive stars scattered across the galaxy in numbers that defy counting. Yet each one is a window into the most extreme conditions the universe can produce. They are killers, yes, but also teachers, showing us the limits of matter and the bending of time. Their very existence challenges us to confront a universe stranger and darker than any myth. And still, these are but the smallest of the monsters. They are the foot soldiers of darkness, countless and deadly. But beyond them lie creatures of greater scale. Between the stellar killers and the giants at galactic centers exists a rare and mysterious class, a bridge between worlds. These intermediate mass black holes are elusive, their existence debated, their nature uncertain. They may hold the secrets of how the largest black holes came to be. From the familiar horrors of stellar mass killers, we now move toward the shadows of the missing link, the intermediate black holes that may reveal the hidden evolution of cosmic predators. These stellar killers, though relatively small compared to the giants at galactic centers, display a diversity that makes them endlessly fascinating and terrifying. Not every stellar mass black hole is born the same way. The fate of a star depends on its mass, its composition, and its environment. Some stars collapse directly into black holes without a visible supernova, vanishing quietly into darkness. Others explode in cataclysms so bright that they outshine their host galaxies before leaving behind the compact remnant. In both cases, the end result is the same: a region of space-time cut off from the rest of the universe, a gravitational predator lying in wait. One of the unsettling truths about these objects is how close they can be. While supermassive black holes lie at the hearts of galaxies, stellar mass black holes can lurk almost anywhere. They can be found in binary systems within a few thousand light-years of Earth, practically in our cosmic backyard. For example, the system known as A0620-00, located in the constellation of the Unicorn, is home to a stellar mass black hole only a few times heavier than the Sun. It flares periodically as it devours matter from its companion star, lighting up the night sky with bursts of X-rays. The idea that such predators exist so near to us reminds us that the universe is not a tranquil place, but a landscape shaped by violence. Another chilling example is V404 Cygni, already notorious for its outbursts. In 2015, it erupted in a series of violent flares that astonished astronomers. The brightness of the system increased by a factor of hundreds in mere hours, a testament to the chaotic feeding frenzy taking place as the black hole consumed its star. Observations revealed jets of material being blasted outward at near light speed, a demonstration that even small black holes can unleash power beyond human comprehension. The unpredictability of such events shows that black holes are not steady machines, but unstable engines capable of sudden bursts of destruction. Beyond individual systems, the sheer population of stellar mass black holes is staggering. If hundreds of millions exist in the Milky Way alone, then billions must populate the universe. Most of them are dark, inactive, and invisible, detectable only when their gravity betrays their presence. Future surveys may reveal many more, but for now, we are left to imagine the unseen hordes drifting through space. They are the ghosts of dead stars, their legacies reduced to gravitational traps scattered across the cosmos. The thought that our galaxy is haunted by so many silent monsters is both thrilling and chilling. Yet despite their terrifying reputation, stellar mass black holes serve as cosmic laboratories. They allow scientists to test Einstein's theory of relativity in extreme conditions. Observing the motions of companion stars, the warping of light, and the timing of X-ray flares provides evidence that space-time truly bends under immense gravity. Every observation confirms predictions made a century ago, yet each discovery also raises new questions. Do black holes truly destroy information? Does the singularity really exist? Or will quantum gravity reveal a hidden structure? These stellar remnants are not just killers, but clues to the deepest mysteries of physics. What makes them even more intriguing is their potential to grow. When two stellar mass black holes encounter each other, they can form a binary pair, orbiting one another in a deadly dance. Over time, they spiral inward, releasing energy as gravitational waves. Eventually, they merge into a larger black hole, releasing a burst of power that can briefly outshine the entire visible universe in gravitational energy. Such mergers are no longer theory. In 2015, the LIGO Observatory detected the first gravitational waves, ripples in spacetime created by the collision of two stellar mass black holes. This discovery confirmed not only their existence, but also their role as dynamic, evolving entities that reshape themselves through violent unions. The detection of gravitational waves opened a new era of astronomy. For the first time, humanity could listen to the universe, hearing the faint echoes of black holes colliding billions of light years away. These signals revealed populations of black holes heavier than expected, suggesting that stars far larger than our Sun had collapsed in the early universe to create them. Each detection told a story of stellar death, collapse, and rebirth as a black hole. These stories are still being uncovered, but they suggest that the life cycle of stars may be more varied and violent than previously imagined. Consider for a moment what these events mean. Two black holes, each perhaps 30 times the mass of the Sun, spiral toward one another for millions of years. In their final seconds, they orbit each other dozens of times per second, their horizons whipping through space at half the speed of light. When they merge, the resulting black hole swallows the last remnants of their individuality, and a burst of gravitational energy equal to several suns converted entirely into waves shakes the cosmos. For us on Earth, the signal is faint, stretching detectors by less than the width of a proton, yet it carries the story of titanic monsters colliding in silence. Stellar mass black holes are thus far more than the silent killers of binary systems. They are participants in cosmic symphonies of destruction and creation. They devour stars, unleash jets, and collide in bursts of space-time ripples. They are the most numerous black holes we know, and their behaviors continue to surprise us. Each observation is a reminder that the universe is alive with violence, that the night sky is a stage upon which invisible players act out dramas of unimaginable scale. And still, as terrifying as they are, they pale in comparison to what comes next. Beyond the realm of stellar mass, black holes lies a more elusive class, a possible bridge between the small killers and the titans at galactic centers. These intermediate mass black holes remain mysterious, rarely glimpsed and poorly understood. If they exist in large numbers, they may hold the secrets of how galaxies themselves were seeded. As we turn from the common killers to the missing links, the shadows deepen and the mysteries grow even greater. Though we now recognize stellar mass black holes as common, their familiarity does not diminish their power to unsettle the imagination. They are the most approachable of cosmic monsters in scale, yet they remind us that death is an essential part of the universe's story. Every one of them marks the end of a star, an end so extreme that light itself is bound forever. When we look at the galaxy through this lens, we see a graveyard scattered with invisible tombs, each one a marker of violent collapse. But unlike ordinary tombs, these do not remain still. They continue to feed, to grow, and to influence their surroundings for billions of years. The process of feeding is not always steady. Many stellar black holes sip from their companions gently, allowing matter to stream steadily into their disks. but others gorge themselves suddenly, pulling in matter in great surges that release terrifying bursts of energy. These violent episodes can light up the sky and have been recorded as sudden, bright X-ray flares lasting days or weeks. The drama of these outbursts speaks to the unpredictable nature of stellar black holes. They can wait silently for centuries, then roar to life in an instant, announcing their presence to any who watch the heavens. We also now understand that stellar mass black holes are more diverse in size than once imagined. While many weigh less than 20 times the mass of the Sun, some discovered by gravitational wave observatories are far heavier, approaching 50 or even 70 times solar mass. Their existence suggests that certain stars in low metal environments, stars born with fewer heavy elements, can collapse directly into heavier black holes without blowing themselves apart. This possibility opens a window into the early universe, when stars were massive, primitive, and capable of creating such remnants in large numbers. Each detection of a heavy stellar mass black hole tells us something new about the lives of the first stars and the violent cosmos in which they lived. The danger these objects pose is not confined to their feeding and flaring. Imagine a stellar black hole drifting unseen through space, ejected from its birthplace by the kick of a supernova. It wanders the galaxy like a rogue predator, invisible except for its gravity. Should such an object pass through a dense region of gas or too near a star system, it could disrupt planetary orbits, strip atmospheres, or trigger collapses of material into its maw. The probability of one wandering into our solar system is small, but not zero. The thought alone is enough to remind us of how fragile our existence is in the wider cosmos. Even when they are not directly threatening us, stellar mass black holes are terrifying in concept. They turn the familiar physics of everyday life into something alien. Gravity, usually gentle and predictable, becomes absolute and crushing. Time, which we measure in steady beats of clocks, becomes distorted, stretched, and warped. Even information, the record of events, is questioned, for we do not yet know if the story of what falls into a black hole is lost forever or somehow preserved at the horizon. These puzzles strike at the core of what it means to know reality. Despite their horrors, there is beauty in how they shape the universe. By devouring stars, they release energy that can trigger new cycles of star formation. By colliding, they send ripples across space-time that we can now detect, giving us new senses to perceive the cosmos. They are participants in a grand cycle, endings that lead to beginnings, destructions that give way to creations. Without them, galaxies would evolve differently, and the cosmic story would lack its most dramatic chapters. Consider again Cygnus the X1. When it was first identified, even Stephen Hawking placed a bet that it would not turn out to be a black hole. So skeptical was he that nature could create such extreme entities. Yet the evidence was undeniable. Decades later, Cygnus X1 remains a symbol of the moment when humanity crossed from theory into reality, from speculation into confirmation. It is more than a binary system. It is a reminder that black holes are not just thought experiments, but neighbors, existing within the same galaxy we call home. V404. Cygni tells a similar story. Its eruptions have been watched by generations of astronomers, each event adding to the sense of awe and dread. It shows that even black holes, only a few times the mass of the Sun, can unleash energies comparable to entire stars. Every flare is a reminder that power in the universe is not always proportional to size. Sometimes, the smallest predators can strike with the greatest violence. Together, these systems illustrate the dual truth of stellar mass black holes. They are ordinary products of stellar death, yet extraordinary in the powers they wield. They are the silent background of the Milky Way, yet capable of shaking our understanding of physics when they collide or flare. They are killers, yes, but also guides pointing us toward deeper truths. And yet, for all their terror, they are not the ultimate black hole story. They are merely the foundation upon which greater mysteries rest. Between the stellar killers and the galactic titans lies a missing link, a category so elusive that only a handful of candidates exist. These intermediate mass black holes may bridge the gap between the common and the unimaginable, holding secrets about how supermassive black holes came into being. As we step beyond the realm of the common killers, we enter the shadows of speculation and rarity, where the next class of monsters waits to be revealed. The cosmos tells its stories across a vast range of scales. We have seen the stellar mass black holes, those killers born from the collapse of stars, weighing a handful to dozens of solar masses. We also know of the supermassive black holes, leviathans lurking at the centers of galaxies, millions or billions of times more massive than the Sun. But between these two extremes lies a curious gap. Logic suggests that there should exist a middle class, black holes weighing hundreds or thousands of solar masses. Yet for decades they remained invisible, leaving astronomers to wonder if nature had skipped this step entirely. These elusive objects are called intermediate mass black holes, the missing link in the evolutionary chain of cosmic predators. The difficulty of finding them lies in their nature. Stellar mass black holes can be discovered in binary systems, where their hunger for a companion star betrays them through bright X-ray flares. Supermassive black holes announce themselves by their sheer gravitational command of entire galaxies. But an intermediate black hole, neither small enough to cling to a single star nor large enough to dominate a galaxy, might wander unnoticed in dark star clusters or the outskirts of galaxies, quiet and faint. For years, astronomers debated whether they existed at all, or whether black holes jumped directly from stellar to supermassive. Hints began to emerge in the most unlikely of places. Globular clusters, those dense balls of ancient stars that orbit galaxies, became prime suspects. Their crowded interiors provide conditions where stellar mass black holes could merge again and again, slowly building into something larger. If such a process occurs, the result would be an intermediate mass black hole at the cluster's heart. Observations of unusual stellar motions in clusters like Omega Centauri have fueled speculation that such a hidden monster resides within, though confirmation remains tantalizingly out of reach. One of the strongest candidates discovered so far is known as HLX-1, located in the galaxy ESO 243-49. This enigmatic source of X-rays was found to be far brighter than expected for a stellar mass black hole, but far too small to be powered by a supermassive one. Its estimated mass is around 20,000 times that of the Sun, squarely in the intermediate range. HLX-1 flares periodically as though consuming a star that passes close to its orbit, providing evidence that it is not a mere illusion, but a genuine black hole of unusual scale. For astronomers, HLX-1 is a glimpse into a class of objects that could reshape our understanding of galactic evolution. If intermediate black holes exist in significant numbers, they may be the seeds from which supermassive black holes grow. Imagine the early universe, filled with massive stars, forming and collapsing into black holes. These black holes gather in clusters, merging again and again until one dominates. Over cosmic time, it swallows more material and merges with others, growing into the supermassive beasts that anchor galaxies today. Without these middle stages, it is difficult to explain how supermassive black holes grew so quickly in the young universe, less than 1 billion years after the Big Bang. The missing link may hold the key to the greatest mystery of all, how the largest black holes came to be so soon. But despite these tantalizing possibilities, the evidence remains fragmentary. For every candidate like HLX-1, There are many ambiguous cases where the data can be explained by other phenomena. Bright X-ray emissions can come from tightly packed stellar systems. Strange stellar motions can be explained by unseen masses of ordinary stars. The hunt for intermediate black holes requires extraordinary precision and patience. Yet the search continues, for the prize is too great to ignore. To find them is to uncover the origin story of the most powerful engines in the cosmos. Intermediate mass black holes sit at the edge of both evidence and imagination, occupying a space where theory suggests they must exist, yet observation rarely confirms them. Their very rarity adds to their aura of mystery. Why are they so hard to find? Perhaps because they live in environments that mask their presence. Unlike stellar mass black holes that light up when devouring a companion, or supermassive ones that dominate galactic centers, intermediate black holes may spend much of their lives in silence. They might reside in the hearts of globular clusters, where their gravitational pull subtly alters the orbits of stars, or in dwarf galaxies too faint for detailed study. In such places, they are ghosts within ghostly systems, hiding in plain sight. The search for these elusive predators has led astronomers to ingenious strategies. One method is to look for X-ray sources too bright to be explained by stellar mass black holes, but too dim to match supermassive ones. Such sources are called ultraluminous X-ray objects, and while many can be explained by exotic accretion processes, some remain suspicious. HLX-1, for example, produces bursts of X-rays consistent with a black hole thousands of solar masses in size. Its variability suggests it is not a steady glow from a star cluster, but the flickering heartbeat of a single powerful object. Another method involves tracing the motions of stars. If a group of stars orbits an unseen mass far heavier than the surrounding stars, the culprit may be an intermediate black hole. Observations of Omega Centauri, the largest globular cluster in the Milky Way, revealed stars moving faster near the core than expected, hinting at a hidden mass. Similar evidence has emerged in other clusters, but the data are never conclusive. Alternative explanations, such as concentrated stellar populations or exotic dynamics, often compete with the black hole hypothesis. Still, the possibility remains that many clusters hide dark hearts within them. Gravitational waves provide yet another avenue for discovery. When two stellar black holes collide, their merger may produce a remnant heavier than either alone, nudging it into the intermediate range. Already, LIGO and Virgo have detected mergers producing black holes of 60 or 70 solar masses, heavier than any seen before. If larger mergers are detected, producing remnants of hundreds of solar masses, it will be direct evidence that intermediate black holes are born not only in the early universe, but continue to form even today. Each detection adds a piece to the puzzle, suggesting that the missing link may not be entirely missing after all. The implications of confirming their existence are profound. If intermediate black holes are common in clusters and dwarf galaxies, then they may serve as stepping stones to the formation of supermassive black holes. In the chaotic early universe, such seeds could have grown quickly, feeding on dense clouds of gas and merging with one another until they became the leviathans we see today. Without these seeds, it is difficult to explain why quasars powered by billion solar mass black holes already existed when the universe was less than 1 billion years old. The missing link may be the bridge that explains how cosmic giants rose so rapidly from primordial darkness. Yet there is another possibility, more unsettling in its own way. What if intermediate mass black holes are rare, even non-existent? What if the universe found shortcuts to build its largest monsters? Some theories suggest that supermassive black holes were born directly from the collapse of enormous gas clouds in the early universe, bypassing the intermediate stage altogether. If this is true, then the absence of intermediate black holes is not a puzzle, but a clue. It would tell us that nature does not always proceed step by step. that sometimes it leaps across scales in a single bound. Such leaps would challenge our assumptions about how gravity sculpts the cosmos. The mystery deepens when we consider how we might ever observe one directly. Unlike M87 star, whose supermassive horizon was imaged by the Event Horizon Telescope, an intermediate black hole would be far smaller and fainter. To resolve, one would require instruments beyond our current capabilities. For now, we rely on indirect signs, the flicker of X-rays, the swirl of stellar orbits, the ripples of gravitational waves. Each hint is like a footprint in the dark, suggesting the presence of a predator we cannot yet see. Intermediate black holes remind us that absence can be as terrifying as presence. We know they should exist. We glimpse their shadows, yet they remain elusive. Their silence is louder than the roars of quasars, their invisibility more haunting than the flares of stellar remnants. They sit between the known and the unknown, between what we can confirm and what we can only suspect. And in that space of uncertainty, imagination thrives. Perhaps they are common, shaping galaxies from the shadows. Perhaps they are rare, freaks of cosmic chance. Either way, their story is bound to the story of the universe itself. As the search continues, we are left with a sense of suspense. The missing link has not yet been fully revealed, but its outline is growing clearer. Each new observation brings us closer to an answer, whether confirming their existence or forcing us to reconsider our models of cosmic evolution. In the end, whether abundant or absent, intermediate black holes will teach us something fundamental about the universe. They are either the seeds of the giants or the evidence that giants were born fully grown. Either way, they shape the way we understand the dark engines that rule galaxies. And as with all black holes, the fascination is inseparable from the fear. If stellar mass black holes are the killers we can count in millions, and supermassive black holes are the titans at galactic hearts, then intermediate black holes are the shadows between, the predators that may stalk the night unseen. They are the missing monsters, and their mystery is part of what makes the universe both terrifying and beautiful. Intermediate mass black holes occupy a strange place in cosmic imagination, for they are not merely a theoretical bridge between the small and the vast. They represent a question of origin. If the universe is filled with supermassive black holes at the hearts of galaxies, then how did they grow so immense so quickly? The early universe was young, barely a few 100 million years old, when the first quasars were already blazing, powered by black holes of billions of solar masses. Ordinary stellar remnants could not have grown that fast by accreting matter alone. Something more efficient must have taken place. Intermediate black holes may be the answer, the stepping stones that allowed the giants to form at a pace that otherwise seems impossible. Picture the early cosmos, still glowing faintly with the afterglow of the Big Bang. The first stars, called population 3 stars, were enormous, hundreds of times more massive than the Sun, and lived for only a few million years. When they died, they may have collapsed into black holes dozens or hundreds of solar masses heavy. In dense regions, these young black holes could collide, forming larger ones. In time, the process could yield black holes thousands of solar masses across, seeds from which supermassive black holes would grow. If this scenario is true, then intermediate black holes are not just missing links, but the very architects of galactic evolution. Yet despite the elegance of this picture, confirming it remains frustratingly difficult. HLX-1 is still the brightest example, but many astronomers hunger for more. Observations of dwarf galaxies have turned up promising candidates, objects too bright and heavy to be explained by stellar black holes, but too small to be considered supermassive. These discoveries hint at a hidden population scattered throughout the cosmos. If true, it means intermediate black holes may be far more common than we realize, shaping galaxies quietly while avoiding direct detection. The future may hold answers. Next-generation observatories, both on Earth and in space, are being designed to capture gravitational waves with greater precision, to track stellar motions with sharper clarity, and to detect faint X-ray sources across the sky. Missions like the Laser Interferometer Space Antenna, scheduled to launch in the coming decades, will be sensitive to lower frequency gravitational waves, the kind produced by mergers of intermediate mass black holes. When such signals are captured, they will provide direct evidence of these missing monsters. For the first time, we may be able to map their population and role in cosmic history. Until then, intermediate black holes remain a riddle written into the structure of the universe. Their absence in current surveys could mean they are rare, or it could simply mean they are masters of disguise, hiding in places we have not yet looked or in ways we do not yet understand. They embody the tension between what theory demands and what observation allows. In that gap lies one of the most tantalizing mysteries of astrophysics. The terror of these objects is not only in their potential size but in their implications. If they are real, then the universe is filled with hidden predators hundreds or thousands of times the mass of the Sun, capable of tearing apart stars and reshaping clusters. If they are not real, then something even stranger must be true, that the universe has found a way to build giants without them. Either answer pushes us deeper into the unknown. Either answer reveals a cosmos more alien than we imagined. As we close the chapter on the missing link, we are left with both awe and unease. We know stellar black holes exist by the millions. We know supermassive black holes dominate galaxies. The intermediate class remains an open question, a shadow on the cosmic map. They may yet emerge as the keystones of cosmic evolution, or they may remain elusive, forever at the edge of discovery. But whether present or absent, their mystery serves its purpose. It drives us forward, pushing science to its limits, reminding us that the universe is never finished revealing its secrets. From the uncertainty of the missing link, we now turn towards certainty of the Titans. There is no doubt about their existence. They are the gravitational hearts of galaxies, the true rulers of the cosmos. Vast beyond comprehension, weighing millions or billions of suns, they shape the fate of galaxies and even the flow of cosmic history. They are the supermassive black holes, the greatest monsters of all, and our journey now leads into their domain. From the scale of stellar remnants and the mystery of the missing links, we now step into the domain of giants. Supermassive black holes are the true monarchs of the universe. They do not lurk invisibly in small binary systems, nor do they drift silently between stars. Instead, they sit at the very centers of galaxies, anchoring billions of stars in their orbits. These monsters are so immense that their gravity shapes entire galactic structures. To speak of them is to speak of the most powerful engines in existence, millions or billions of times more massive than the Sun, ruling from the dark hearts of galaxies. Astronomers once wondered why stars at the center of the Milky Way moved so quickly, their orbits tight and precise, as though whipped around by an unseen hand. Careful observation of these stellar dances revealed the truth. An object 4 million times the mass of the Sun lies at our galactic center. This object, known as Sagittarius, a star, is invisible except for the radio waves it emits. No cluster of stars could mimic its pull, no ordinary mass could explain its dominance, only a supermassive black hole could. With this discovery, the idea of galactic hearts became undeniable. Every large galaxy we observe, from spirals to ellipticals, appears to hide such a monster in its core. The sheer scale of these entities defies comprehension. Imagine compressing millions of suns into a volume smaller than our solar system. Their horizons span billions of kilometers, yet compared to the galaxies they command, they are small, like a grain of sand controlling a beach. The paradox lies in their subtlety. Despite their titanic masses, they remain unseen unless feeding. When they awaken, however, they unleash energies that can rival or exceed the combined light of all the stars around them. Sagittarius. A star is relatively quiet today, but it has not always been so. Evidence suggests that in the past, it flared brightly, consuming matter and lighting up the galaxy's core. If it were to awaken again, the night sky would change dramatically, with our galactic heart blazing across the heavens. This quiet predator at the center of our Milky Way is a reminder that even when dormant, supermassive black holes hold immense potential for violence. Part of what makes them terrifying is their longevity. While stellar black holes mark the end of stars, supermassive ones have lived for billions of years, growing steadily as galaxies evolved. They consume gas, stars, even entire clusters, and every victim adds to their mass. When galaxies collide, their central black holes spiral together in a dance lasting millions of years before merging into something even larger. In this way, supermassive black holes evolve alongside galaxies, shaping their histories in profound and often destructive ways. Perhaps the most dramatic confirmation of their reality came in 2019, when the Event Horizon Telescope captured the first direct image of a black hole's shadow. The subject was not Sagittarius, a star, but a far larger monster at the heart of the galaxy, M87. With a mass 6.5 billion times that of the Sun, this giant was revealed as a dark circle surrounded by a halo of glowing plasma, its gravity bending light itself into a ring. That image was more than a picture. It was a moment of confrontation, humanity staring into the abyss and finding it real. The shape matched predictions of Einstein's relativity perfectly, showing that even in the most extreme conditions, space-time obeys the rules of his theory. And yet, these titans are not merely passive rulers. They are creators and destroyers in equal measure. When they feed greedily, their accretion disks blaze with radiation across the spectrum, from radio waves to X-rays. They launch jets of material thousands of light years into space, beams so powerful they sculpt entire galaxies. These outflows can prevent new stars from forming, shutting down stellar nurseries and altering the course of galactic evolution. A single supermassive black hole, though small compared to its galaxy, can dominate its fate. To stand at the edge of such a being, were it possible, would be to witness gravity on a scale beyond imagination. The horizon of M87's black hole would swallow our entire solar system, sun and planets alike, in silence. The tidal forces near such giants are less extreme than near stellar black holes, but their size makes escape impossible long before one reaches the singularity. They are not quick killers, but patient traps, slowly pulling everything toward their inexorable centers. Supermassive black holes embody both extremes of cosmic nature. They are silent when quiescent, nearly invisible, and yet they can awaken as quasars, blazing brighter than all the stars in their host galaxies combined. They are symbols of permanence, persisting across billions of years, and yet they are engines of change, reshaping galaxies through violence. To study them is to study the very structure of the universe itself, for their influence extends across scales too vast for the human mind to easily grasp. From Sagittarius, a star, to the titanic shadow of M87 star, these monsters remind us that the universe is ruled from its centers by forces of darkness. They are terrifying not because they are rare, but because they are universal. Every galaxy we see holds one, and without them, the galaxies themselves might never have taken shape. The missing links may remain elusive, but the giants are undeniable. They are here, they are ancient, and they are still hungry. From the galactic hearts we know, we must next confront their brightest and most terrifying manifestations. When supermassive black holes awaken fully, they become quasars, blazing beacons visible across the universe. Their light can outshine trillions of suns, and their hunger can shape entire epochs of cosmic history. If the quiet rulers of galaxies inspire awe, the raging hearts of quasars inspire terror, for they are destruction transformed into light itself. Supermassive black holes are not only the anchors of galaxies, but also the arbiters of their destiny. Astronomers now understand that the growth of galaxies and the growth of their central black holes are intertwined. This connection is seen in the remarkable correlation between the mass of a galaxy's bulge and the mass of its central black hole. The larger the galaxy, the larger the black hole that rules it. This relationship suggests a feedback loop. As the black hole grows, it regulates star formation in its host galaxy, and as the galaxy evolves, it feeds its black hole with new material. The two are locked in a cosmic dance, each shaping the other across billions of years. One of the most astonishing features of these giants is their ability to unleash jets that stretch across thousands of light years. These beams of plasma are accelerated to nearly the speed of light and can extend well beyond the edges of their host galaxies. Seen through radio telescopes, they appear as colossal structures, dwarfing entire star systems, glowing as particles within them spiral through magnetic fields. The origin of such jets remains one of astrophysics' most fascinating mysteries. We know they are powered by the twisting of magnetic fields around the spinning black hole, yet the precise mechanics remain elusive. What is clear is their impact. Jets can heat surrounding gas, preventing it from cooling into stars, or in some cases trigger new bursts of star formation by compressing clouds. These titanic outflows show that supermassive black holes are not silent prisoners of gravity, but active sculptors of galactic life. The story of M87 star is perhaps the most dramatic demonstration of this. Not only was it the first black hole ever imaged, but it is also famous for its enormous jet, a structure thousands of light years long that has been studied for decades. This jet is visible even in optical light, a thin streak cutting across the galaxy, carrying energy far into intergalactic space. To see it is to witness the scale of influence a single black hole can command. The fact that this power comes from an object smaller than our solar system is a reminder of the strange compression of scales that black holes embody. Small in size, infinite in influence. Closer to home, Sagittarius A star offers a quieter portrait, but it too bears scars of past activity. Observations have revealed vast bubbles of gamma-ray emission extending above and below the Milky Way's disk, structures so large that they span tens of thousands of light years. These so-called Fermi bubbles are believed to be remnants of a past eruption from our galaxy's central black hole, a time when it fed more vigorously and expelled matter in colossal outflows. Today it slumbers, nibbling occasionally on stray gas clouds, but the evidence of its violent youth still glows faintly across the sky. The physics of supermassive black holes pushes the boundaries of theory. Their horizons are vast, their gravity absolute, yet near their centers, quantum effects may play a role. The singularity at their heart is still beyond comprehension, a place where relativity and quantum mechanics collide. The mystery of what lies within drives physicists to search for a theory of quantum gravity, a framework that can describe space-time at its most extreme. In this way, supermassive black holes are not only astronomical objects, but also philosophical challenges, forcing us to confront the limits of human knowledge. What is perhaps most humbling is the inevitability of their rule. Galaxies form, stars are born and die, planets emerge and vanish, but the black hole at the center endures. Over billions of years, it will continue to feed, to merge, and to grow, even as the galaxy around it changes. Eventually, when stars fade and gas is consumed, the black hole may be one of the few things that remain, a monument to cosmic time itself. These galactic hearts are not just temporary actors in the play of the universe. they are its most enduring rulers. And still, their quiet dominion is not the end of the story. For when they awaken fully, when they gorge themselves on torrents of matter, they transform into the brightest objects in the universe. These are quasars, supermassive black holes blazing with the fury of galaxies, their light reaching across billions of light years. They are not only powerful, but almost incomprehensibly so, visible from the dawn of time, their radiation outshining entire galaxies. To face a supermassive black hole is to see the quiet heart of a galaxy. To face a quasar is to witness the heart ablaze with destruction and creation, a beacon of cosmic violence. Supermassive black holes confront us with a paradox. They are invisible by nature, defined by their ability to trap light, and yet they are also responsible for some of the brightest phenomena in the universe. The glow we associate with them does not come from the black hole itself, but from the matter that falls toward it. Gas, dust, and even whole stars are shredded into spiraling torrents, forming accretion disks that reach temperatures of millions of degrees. This incandescent plasma blazes across the electromagnetic spectrum, releasing energy more powerful than the combined light of billions of suns. To witness such a display would be to see destruction transformed into radiance. The power of supermassive black holes lies not only in their capacity to consume, but also in their ability to orchestrate cosmic order. Entire galaxies revolve around them, and their activity influences the growth of stars on scales far beyond their immediate vicinity. Astronomers now believe that the evolution of galaxies cannot be understood without acknowledging the role of their central black holes. They are not passive inhabitants of galactic centers, but engines of regulation, deciding when stars may flourish and when they must fade. This realization reframes them from being solitary monsters to being cosmic architects, shaping the universe on scales we are only beginning to understand. And yet, for all their grandeur, they remain terrifying. The idea of a singularity at their core, where density becomes infinite and the known laws of physics collapse, remains unresolved. The event horizon is the ultimate veil, preventing us from ever glimpsing what happens within. Theories suggest that information may be preserved at the horizon in subtle quantum states, but no experiment has yet resolved the paradox. Supermassive black holes remind us of the limits of knowledge, that there are places in the cosmos where certainty ends and mystery begins. For many, this is the true terror. Not only the destruction they bring, but the silence of the unknown they embody. Among the most astonishing examples of these titans is TON 618, an ultramassive black hole weighing an estimated 66 billion times the mass of the Sun. Its scale is nearly beyond imagination. If placed at the center of our solar system, its event horizon would extend past the orbit of Neptune. To speak of such an object is to confront something that dwarfs our capacity for comparison. TON 618 is not merely a monster, it is a revelation of what the universe is capable of, a demonstration that nature can forge entities of a scale that seems almost impossible. And it is only one among many. The census of ultramassive black holes is incomplete, and there may be others even larger hidden in the depths of space. For all their terror, supermassive black holes also inspire a strange kind of awe. They are enduring, ancient, and inescapable. They take what is given to them and return it as light, jets, and order on galactic scales. They are the quiet rulers of cosmic time, beings that outlive stars, planets, and perhaps civilizations. To imagine them is to imagine the ultimate persistence, a presence that endures even as the universe changes around them. Yet as mighty as they are not the final word in cosmic terror. For when they awaken in full fury, consuming matter at a rate that pushes the limits of physics, they ignite as quasars, blazing across billions of light years. Quasars are the brightest beacons of destruction, the most dazzling expressions of the hunger of black holes. If supermassive black holes are galactic hearts, then quasars are those hearts on fire, visible across cosmic history as warnings and as wonders. To understand the full terror of black holes, we must turn next to these blinding titans, the quasars that announce their presence to the entire universe. If supermassive black holes are the quiet rulers of galaxies, then quasars are those rulers awakened in fury. A quasar is what happens when a supermassive black hole feeds so voraciously that its accretion disk blazes brighter than all the stars in its host galaxy combined. These cosmic beacons are among the most luminous objects in the universe, their light visible across billions of light years, reaching us from epochs when the universe was young. To gaze upon a quasar is to look back in time, witnessing not only the hunger of a black hole, but also the dawn of cosmic history. The discovery of quasars in the 1960s startled astronomers. These strange point-like sources in the sky shone with the brilliance of entire galaxies, yet appeared as tiny dots through telescopes. Their spectra revealed redshifts so extreme that they must be impossibly far away, billions of light years distant. The only explanation for their power was accretion onto supermassive black holes. For the first time, humanity realized that black holes were not only invisible predators, but also the engines behind some of the brightest lights in the cosmos. The physics of a quasar is straightforward in principle, yet staggering in scale. Gas falling into the accretion disk heats to millions of degrees, releasing energy as it spirals inward. Magnetic fields twist and snap, launching jets that can extend hundreds of thousands of light years into intergalactic space. The radiation from a quasar is so intense that it can strip electrons from atoms across vast regions, altering the chemistry of galaxies. The sheer violence of this process transforms black holes from silent traps into cosmic lighthouses, blazing across the universe with unmatched intensity. Some quasars are so powerful that they outshine not just their galaxies, but thousands of galaxies combined. TON 618, one of the most massive black holes known, powers a quasar 66 billion times the mass of the Sun. Its light has traveled 10 billion years to reach us, a signal from a time when the universe was less than 1/3 of its current age. To contemplate such an object is to feel the immensity of cosmic hunger, a black hole that has consumed more matter than we can easily imagine, blazing with a brightness beyond comprehension. Quasars also serve as cosmic probes. Because they are so luminous, their light can be studied as it passes through intervening gas clouds on its journey to Earth. By analyzing the absorption lines in quasar spectra, astronomers have mapped the distribution of matter in the early universe, tracing the web of gas that later condensed into galaxies. In this way, quasars illuminate not only their own nature, but the structure of the cosmos itself. They are both destroyers and messengers, carrying the imprint of cosmic history across billions of years. The terror of quasars lies not only in their power, but also in their implications. If such monsters were once common, then the early universe was far more violent than our own. Galaxies must have grown under the glare of blazing hearts, their stars born and destroyed under the watch of feeding black holes. The fact that quasars are rare today suggests that most supermassive black holes have exhausted their easy supplies of fuel, entering quieter phases. Yet their light remains, reaching us across the abyss, reminders of an age of cosmic fire. From the blazing radiance of quasars, the story of black holes takes another turn. These titans may be the brightest objects in the sky, but they are not the only spectacle of black hole power. For when black holes come in pairs, locked in orbital embraces, They create phenomena even stranger, collisions that send tremors through the very fabric of space-time. From the radiant fury of quasars, we must now turn to the hidden violence of binary black holes, where the universe itself quakes from their final dance. Quasars embody the paradox of black holes at their most extreme. Objects defined by darkness, yet revealed to us through overwhelming light. They are both void and furnace, silence and raw. For a galaxy caught in the grip of an active quasar, the experience is transformative. Clouds of gas that might otherwise collapse to form new stars are swept aside by the intense radiation pouring from the accretion disk. Jets carve through interstellar space, heating and disrupting the delicate balance of a galaxy's ecosystems. In some cases, this feedback halts star formation altogether, leaving galaxies to age quietly under the rule of their central monster. In others, the shock waves compress clouds into bursts of star birth, paradoxically using destruction as a tool of creation. This dual role makes quasars central to the story of cosmic evolution. They are not isolated phenomena, but key players in the shaping of galaxies. When astronomers look back into deep time, peering at galaxies, when the universe was only a fraction of its current age, they often find quasars blazing at their cores. These luminous engines tell us that supermassive black holes grew quickly, reaching billions of solar masses in less than a billion years. Such rapid growth challenges our understanding of black hole formation. Were they seeded by the mergers of stellar remnants? Were they born directly from the collapse of enormous primordial clouds? The existence of quasars demands answers, for their very presence in the young cosmos defies simple explanations. Observationally, quasars are diverse, yet all share the same underlying engine. Some shine primarily in visible light, appearing as brilliant star-like points. Others blaze more strongly in radio waves, their colossal jets extending far beyond their host galaxies. Still others dominate in X-rays, the glow of matter spiraling at relativistic speeds into the abyss. Each wavelength offers a different view, a different angle on the fury of accretion. Together, they build a picture of a phenomenon that is at once terrifyingly violent and exquisitely ordered, a machine of nature operating with ruthless efficiency. The sheer brightness of quasars is difficult to convey. Consider that the Milky Way contains hundreds of billions of stars, each contributing its small share of light. A quasar can outshine it 1,000-fold, its brilliance concentrated into a volume no larger than our solar system. If such a thing were to erupt in our galaxy, it would outshine every star in the sky, turning night into perpetual day. Life as we know it would be impossible within thousands of light years of such a monster. Quasars remind us that black holes are not distant curiosities, but forces that could, under the right conditions, erase habitability across vast stretches of space. The discovery of quasars also reshaped how we think about the universe itself. Because they are so luminous and so distant, they became beacons for mapping cosmic expansion. By measuring their redshifts, astronomers traced the growth of the universe and confirmed its accelerating pace. In this sense, quasars are not only markers of black hole fury, but also signposts of cosmic history. They connect the smallest scales of physics, the dance of particles near an event horizon, to the largest scales of cosmology, the expansion of the universe itself. And yet, their rarity today offers a strange kind of comfort. Quasars were common in the early universe, but most have faded as their black holes ran out of nearby fuel. The Milky Way's own central black hole slumbers, unlikely to flare as a quasar in our era. But the possibility remains. A collision with another galaxy, such as the predicted merger with Andromeda billions of years from now, could awaken Sagittarius A star into a quasar phase, lighting the sky with brilliance unseen in human history. That prospect is both terrifying and exhilarating, a reminder that the monsters at galactic hearts are never truly gone. From quasars, we learn that black holes are not confined to invisibility. They can announce themselves as the brightest lights in the cosmos, reminders of hunger written in starlight. But brightness is not the only form of terror they command. When black holes pair together, when they spiral inward in dances that last millions of years, their final unions release energies unlike anything else in nature. These binary black holes do not blaze with light, but with gravity itself, sending ripples across space-time. From radiant quasars, we now descend into the silent but earth-shaking domain of black hole collisions, where the universe trembles with the force of their embrace. Quasars remain one of the most haunting reminders that the universe is not a calm or balanced place, but a stage for extremes. In their brilliance lies the evidence of unimaginable destruction, and in their distance lies the story of a younger cosmos filled with fire. Every photon that reaches our telescopes from a quasar has traveled across billions of years, carrying with it the imprint of a time when galaxies were still in their infancy. To observe one is to open a window onto the past, to see creation and annihilation intertwined at scales beyond comprehension. Among the most staggering of these cosmic lighthouses is TON 618. With a black hole mass estimated at 66 billion suns, it may be the most massive known. Its light began its journey when Earth was still forming, long before life emerged. Even today, as its radiation washes across our detectors, we are witnessing an event that unfolded in a universe half its present age. TON 618 is not merely a quasar, it is a testament to how quickly black holes can grow when conditions are right, devouring gas and stars with such appetite that they become the dominant forces of their galaxies. If such an object can exist, then the limits of black hole growth may be far higher than we once believed. Quasars also demonstrate the unity of destruction and beauty. Their light is terrible in its origin, the glow of matter torn apart at near light speed, yet it allows us to chart the structure of the universe. By examining quasar light as it passes through cosmic gas clouds, astronomers can detect the fingerprints of hydrogen and heavier elements. This mapping reveals the cosmic web, the vast network of filaments that stretches across space, connecting galaxies like beads on a string. Without quasars, this hidden scaffolding of the cosmos would remain invisible. In their destruction, they grant us vision. The sheer rarity of active quasars in our current cosmic epoch is a reminder of time's relentless passage. What was once common is now exceptional. The universe is quieter today than it was billions of years ago, and most supermassive black holes have entered dormant states. Yet their capacity for awakening remains. Should a galaxy collision funnel new fuel into their hearts, they will ignite once more, and the sky will blaze anew. The thought that galaxies like our own could one day flare as quasars again is a reminder that the peace of the present is temporary. The universe remembers violence, and violence can return. For all their brightness, quasars are but one manifestation of black hole power. They are the outward spectacle, the showpiece of feeding giants. But there is another arena where black holes express their fury, one hidden from the eye but felt across the fabric of existence itself. When two black holes become bound together, when their orbit tightens over millions of years, their final collision releases more energy in an instant than all the stars in the universe shining at once. This energy does not appear as light, but as waves in space-time, ripples that race across the cosmos. The story of black holes now shifts from fire to tremor, from brightness to vibration. We leave behind the blazing quasars, whose light reaches us like ghostly torches from the past, and move into the realm of binaries, where collisions are foretold in spirals of inevitability. These binary black holes are the heralds of gravitational waves, signals that we have only just begun to detect. With them, a new chapter of astronomy has opened, one where we can not only see the universe but hear it. And what it whispers is a tale of monsters colliding in the dark, shaking the very foundations of reality. When two black holes find one another, the result is one of the most dramatic stories the universe can tell. These monsters, each born from collapse and silence, become locked in an embrace that can last for millions or even billions of years. At first, their dance is wide and slow, the pull of gravity binding them but leaving space between. Over time, they spiral closer, releasing energy in a form invisible to human eyes. Gravitational waves, ripples in the fabric of space-time itself. The closer they come, the faster they orbit, until in their final moments they circle each other dozens of times per second. Then, in an instant, they merge, forming a new black hole and unleashing a pulse of energy so great that it briefly outshines the combined light of every star in the universe. For decades, these cosmic collisions were only theoretical. Einstein's equations of general relativity predicted that orbiting masses would create ripples in space-time, but the waves were thought to be too faint to ever detect. Astronomers built instruments, waited, and hoped, but for nearly a century, the idea remained unproven. That changed in 2015, when the Laser Interferometer Gravitational Wave Observatory, known as LIGO, captured a faint signal from across the cosmos. The chirp lasted only a fraction of a second, but it told a story of two stellar mass black holes, each about 30 times the mass of the Sun, colliding more than 1 billion light-years away. Humanity had, for the first time, heard the sound of black holes merging. The importance of this discovery cannot be overstated. It confirmed that gravitational waves were real, opening a new sense with which to explore the cosmos. No longer limited to light, we could now listen to the universe itself, detecting events invisible to telescopes. Each new detection added to the story, revealing populations of black holes heavier than expected, suggesting that stars in the early universe collapsed into more massive remnants than those we see today. The universe, it seemed, was filled with collisions, each one sending out echoes that travel across time and space to reach us. The terror of binary black holes lies in their inevitability. Once bound, their spiral cannot be stopped. They will circle each other ever faster, radiating away their orbital energy until they collide. Imagine two objects tens of kilometers across but weighing as much as dozens of suns, circling each other at half the speed of light. In their final milliseconds, they release energy equivalent to several suns converted entirely into gravitational waves. This burst briefly outshines the combined light of the visible universe, not in photons, but in ripples of space-time. For any beings close enough to witness, the event would be catastrophic beyond imagining. And yet, these collisions are not rare. LIGO and its European counterpart Virgo have now detected dozens of them, each a whisper from billions of light-years away. With every detection, the universe grows louder, revealing a population of binary black holes scattered across space. Some may be born in stellar nurseries, others in the crowded hearts of clusters where close encounters bind them together. In the chaos of galaxy collisions, supermassive black holes too can form binaries, though their dances last far longer and their mergers remain beyond the reach of our current instruments. One day, with future detectors like the Laser Interferometer space antenna, we may hear the deep bass notes of these titanic unions, the mergers of millions or billions of solar masses. The beauty of gravitational waves is that they are unfiltered. Unlike light, which can be absorbed or scattered, these ripples pass through everything unimpeded, carrying with them a pristine record of their origin. Each signal is a message written in space-time itself, telling us the masses of the colliding black holes, their spins, their distance, even hints about the environment in which they formed. To listen to them is to hear the secret life of the universe, events hidden from every other form of observation. But with this knowledge comes awe and dread. We now know that the cosmos is filled with collisions on scales that dwarf all human comprehension. These are not rare catastrophes, but common events, the background music of the universe. For every whisper we detect, countless others ripple past us, unnoticed but real. Reminders that the universe is alive with violence. Binary black holes are not exotic exceptions. They are the rule, the inevitable consequence of stars living, dying, and collapsing into darkness. From the first chirp of two stellar remnants merging to the anticipated roar of supermassive unions, the story of binary black holes is still unfolding. They remind us that the universe is not static, but dynamic, not peaceful, but in motion. Every merger is both an end and a beginning, a death and a rebirth. The monsters join together, and from their union, a new one is born, heavier, hungrier, and destined to repeat the cycle. From these cosmic collisions, we move now toward another realm of terror. If binaries reveal themselves through their gravitational roars, there are others that reveal nothing at all. Not all black holes are bound to stars or galaxies. Some are wanderers, flung into interstellar space, drifting unseen and unstoppable. These rogue black holes are the ultimate predators, invisible and silent, capable of passing through the galaxy like shadows. To them we now turn, leaving behind the roaring collisions to confront the menace of the unseen. Binary black holes remind us that gravity is not just a force that binds, it is also a force that drains, slowly bleeding energy from the orbit of paired monsters until their fate becomes unavoidable. Each revolution, no matter how faint, sends ripples outward. At first the waves are gentle, carrying away minuscule amounts of energy, but across millions of years they add up. The orbit shrinks, the dance accelerates, and the black holes grow closer. By the time they near collision, their spirals are so rapid that space itself quivers. In those final moments, the black holes are orbiting each other dozens of times per second, moving at half the speed of light before collapsing into one. For a long time, such mergers were invisible. We could imagine them, calculate them, predict them, but never witness them. LIGO changed that forever. The first detection, known as GW150914, was a signal lasting less than a second, yet it carried more information than decades of theory. It told us of two black holes, 36 and 29 solar masses, colliding over 1 billion light-years away. In that instant, 3 suns' worth of mass was converted into gravitational energy, released in a single burst. The Earth trembled at scales smaller than a proton, but that trembling was enough to confirm that the universe speaks in gravity. Since then, dozens of detections have been made. Each is unique. Some involve pairs of nearly equal mass, others of mismatched partners. Some seem to spin chaotically, others aligned in graceful order. These details matter because they hint at origins. Did the binaries form together as stars, collapsing side by side? Or did they meet later in the crowded cores of clusters where close encounters bound them by chance? Each signal is like a fingerprint, a record of the lives and deaths of stars that ended in darkness. The terror of these events comes not only from their violence but also from their scale. Imagine an explosion so powerful that it outshines all the stars in the visible universe combined, yet no light is produced. Only gravity itself carries the message. The idea that such events happen regularly, scattered across space and time, fills the cosmos with silent catastrophes. We do not see them. We do not hear them. We only feel their faint echoes rippling through us as space-time itself bends and stretches. The collisions of stellar mass black holes are already staggering, but there is a greater spectacle waiting. the mergers of supermassive black holes. When galaxies collide, their central monsters fall into orbit around one another, beginning dances that can last billions of years. Stars are slingshotted away, gas is stirred into chaos, and the black holes spiral closer. When they finally merge, the burst of gravitational waves will dwarf anything we have yet detected, a deep bass note in the symphony of the universe. Current detectors cannot hear such low frequencies, but the upcoming laser interferometer space antenna will. With it, humanity will one day listen to the groaning of space-time as titans collide, revealing the hidden life of galaxies themselves. Binary black holes are therefore more than curiosities. They are milestones in cosmic history. Each collision marks the end of two lives and the beginning of another, larger one. They are the mechanism by which black holes grow, the engines that drive their evolution. And because gravitational waves travel unimpeded, they offer a record untouched by intervening matter. Light can be blocked, but gravity cannot. In this way, binary black holes grant us the most direct evidence possible of the violence of the universe. Yet even with this knowledge, there is a chilling thought. If mergers of stellar black holes are common and mergers of supermassive black holes inevitable, then the cosmos is filled with these events at every scale. We are surrounded not by silence, but by a constant background hum of gravitational waves, too faint for us to hear, yet present all the same. The universe itself is vibrating with the echoes of countless collisions. The calm of the night sky is an illusion. Behind it lies a symphony of violence. From these roaring unions, we turn next to a quieter, but equally terrifying prospect. Not every black hole is bound to a companion or a galaxy. Some are set adrift, wandering alone through the darkness, invisible and undetectable until too late. These rogue black holes may be rarer than binaries, but their menace is unique. They do not announce themselves with light or waves. They simply drift, waiting to cross paths with whatever lies in their way. The final moments of a binary black hole merger defy ordinary imagination. As the two horizons approach, space-time itself becomes chaotic, rippling and stretching in ways no human mind can fully picture. The event horizon of each black hole distorts, elongated like liquid surfaces pulled by tides, until at last they touch and fuse. In that instant, a new horizon forms, smoother and larger, encompassing both. The violence of the merger radiates outward as gravitational waves, shaking the universe like a struck bell. Within seconds, the turbulence settles, and the newborn black hole takes on its final form, larger and quieter, but forever changed. What makes these events so haunting is their invisibility. There are no flashes of light, no bursts of color to dazzle telescopes. The collision of two black holes is a silent affair, hidden entirely within horizons. Only the waves in space-time announce what has happened, faint whispers that cross billions of light years. By the time they reach Earth, they are so subtle that only the most sensitive instruments can detect them, stretching and squeezing our planet by less than the width of an atomic nucleus. And yet, within those faint shifts lies the record of unimaginable destruction. The aftermath of such mergers raises new questions. The resulting black hole is larger than either parent, but it also inherits their spins and momenta in complex ways. Some mergers produce rapidly rotating monsters spinning near the maximum speed allowed by relativity. Others recoil violently, ejected from their surroundings at thousands of kilometers per second, the result of asymmetric gravitational wave emission. Such kicked black holes may wander into intergalactic space, lonely wanderers born from cosmic unions. Each merger is not only an end, but a beginning, producing outcomes as varied as they are terrifying. The study of these collisions has also changed how we think about time itself. Gravitational waves travel at the speed of light, carrying messages across epochs. When we detect a merger today, we are witnessing something that happened billions of years ago, long before Earth formed. Each signal is a relic, a fossilized event carried across space-time to reach us. The realization that our instruments can record the death throes of monsters from before our planet's birth is both humbling and unsettling. We are listening to ancient catastrophes written into the very fabric of reality. Even more haunting is the thought of what lies beyond our reach. Stellar mass black hole mergers are within our grasp, but supermassive mergers remain silent for now. Their gravitational waves are too low in frequency, their collisions too slow for ground-based detectors like LIGO to hear. And yet, the universe must be full of them. Every galactic collision we see is a prelude to such a union. The giants we observe circling each other in distant galaxies are destined to merge, releasing gravitational roars that will one day shake the cosmos. With future instruments, we will hear them, and the universe will grow louder still. Binary black holes show us that black holes are not solitary reapers, but participants in grander dramas. They meet, they spiral, they merge, and they create new monsters, heavier and hungrier. Their collisions are milestones in cosmic history, moments of transformation that echo across time. They remind us that the universe is restless, that gravity never sleeps, and that destruction and creation are inseparably linked. But while binaries reveal themselves through their gravitational songs, there are other black holes that leave no such trace. They do not merge, they do not blaze, they do not shine. They drift alone, invisible except for their gravity, wanderers cast adrift by cosmic violence. These rogue black holes are perhaps the most terrifying of all, for they are predators without warning, capable of appearing in the path of any star system, even our own. From the roaring collisions of binaries, we now turn to the silent menace of these wanderers of the cosmos. Most black holes live tethered to galaxies, bound by gravity to the vast systems of stars and gas that gave them birth. Some dwell at the centers, supermassive monarchs ruling with invisible force. Others remain in binaries, feeding from companion stars or drifting among clusters. But not all stay bound. Some are cast adrift, hurled into interstellar or even intergalactic space, stripped of companions and homes. These are rogue black holes, wanderers of the cosmos, and they are among the most terrifying creatures imaginable. The creation of a rogue black hole is itself an act of violence. When two galaxies collide, their central black holes may spiral toward one another, but the merger is not always symmetrical. If the gravitational waves radiate unevenly, the new black hole may be kicked away at tremendous speeds, thousands of kilometers per second. In some cases, the recoil is strong enough to eject it entirely from its host galaxy, sending it drifting alone through intergalactic voids. Stellar black holes, too, can be flung from their birthplaces by the asymmetric blast of a supernova, gaining velocities sufficient to escape their star clusters. The result is a dark predator without orbit, roaming the universe freely. What makes rogue black holes so frightening is their invisibility. Without a companion star to feed on, or a dense gas cloud to consume, they emit no light. They are utterly dark, detectable only through their gravitational influence on what passes near them. A rogue black hole wandering through interstellar space would be indistinguishable from emptiness until its pull distorted the path of nearby stars, or bent the light of background objects through gravitational lensing. Only in rare alignments have astronomers glimpsed possible rogues, their presence betrayed by the way they magnify distant starlight. But the population must be immense. Estimates suggest our galaxy alone may harbor millions of black holes, many unbound and wandering unseen. Imagine the menace of such an object drifting silently toward our solar system. It would not announce itself with light or heat. It would arrive invisibly, its gravity slowly perturbing the orbits of comets, tugging at planets, and perhaps even tearing Earth from its course. A direct encounter with its event horizon would be catastrophic, but even a near miss could destabilize our planetary system. Though the odds are low on human timescales, the thought that rogue black holes wander the galaxy as unseen threats is enough to provoke unease. Their danger is not confined to disruption. Should a rogue black hole pass through a dense cloud of interstellar gas, it could briefly awaken, feeding on the material and emitting X-rays that would betray its presence. But such an awakening would be temporary, a flicker of activity in an otherwise dark existence. Most wander silently, reminders that the universe is filled with hidden hazards we may never map fully. To live in a galaxy rich with rogue black holes is to live in a landscape of invisible predators. And yet, as with all black holes, their menace is accompanied by mystery. If we could detect them in large numbers, they might reveal the true history of stellar death in our galaxy. Each rogue is a record of a star's life and death, an echo of ancient violence written into the fabric of space. By studying their population, we could learn about the distribution of massive stars, the dynamics of supernovae, and the collisions that shaped galaxies. Even in silence, they are teachers. From the terror of rogue wanderers, we are led closer to home. For while most of these unseen killers drift in distant parts of the galaxy, a few lie surprisingly near. Recent discoveries suggest that the closest black holes to Earth are not in distant galaxies or violent quasars, but in our own neighborhood. Hidden among the stars, we see each night. These nearby threats are quiet, dormant, and almost invisible, but their very proximity makes them especially unsettling. To understand the menace within our reach, we must now turn to the closest threats, the black holes that lurk not in distant galaxies, but in our own celestial backyard. Rogue black holes carry with them a loneliness that feels almost as terrifying as their destructive power. A stellar mass black hole born from a collapsing star often begins life with companions, a sibling star in a binary or a home inside a crowded cluster. But the violence of a supernova or the gravitational chaos of a galactic merger can strip it of all attachments. Cast into the emptiness, it drifts silently, unseen, destined to wander until the end of time. These solitary journeys make rogue black holes some of the most haunting figures in the cosmos. Monsters without thrones, predators without lairs, forever adrift. The sheer number of such wanderers is staggering to consider. If our Milky Way contains hundreds of millions of stellar black holes, then statistical models suggest that millions must be unbound, roaming free between the stars. Most are likely only a few times heavier than the Sun, but some could be tens of solar masses, and others may even reach intermediate scales if they were born from repeated collisions. Each one is invisible unless it happens to pass in front of a distant star, where its gravity acts like a lens, magnifying the background light. A handful of such lensing events have been detected, giving us the first glimpses of solitary black holes. But these rare alignments hint at an unseen population far larger than we can count. One such detection came in 2022, when astronomers announced the discovery of what may be a solitary black hole drifting through the Milky Way about 5,000 light-years away. The object revealed itself only through the precise bending of starlight, an effect so subtle it required years of careful measurement with the Hubble Space Telescope. This lone predator, perhaps 7 times the mass of the Sun, is moving silently through our galaxy, a stark reminder that the darkness around us is populated not only by stars, but by invisible corpses of stars long dead. The menace of rogue black holes lies not in their rarity, but in their stealth. A star or a supernova announces its presence with light, but a rogue does not. It could pass within a few light years of Earth, without any sign, until its pull disturbed the orbits of nearby objects. Even at such distances, the gravitational effects could be profound. nudging comets from the outer solar system into inward journeys or subtly altering planetary paths. A closer approach would mean catastrophe, yet we have no reliable census, no map of these wanderers. They remain hidden, ghosts against the backdrop of space. There is also the question of supermassive rogues. When galaxies collide, their central black holes may merge, but as we have seen, the recoil from gravitational waves can eject the product. If the kick is strong enough, the newborn black hole may escape the galaxy entirely. Such an object, millions or billions of times the mass of the Sun, would drift into intergalactic space, unmoored, dragging with it a cluster of bound stars. These wandering quasars would appear as faint, displaced lights in the void, and a few candidates may already have been spotted. To think of such titans adrift in the abyss is to realize that even the largest monsters are not immune to exile. And so, the universe is likely seeded with wanderers, both small and large, moving invisibly through the dark. They are reminders that stability is fragile, that gravity can bind but also cast away. They are also reminders of our own vulnerability. For even if the probability is small, the possibility exists that one day a rogue black hole could cross paths with our solar system. It would not be malicious. It would simply follow the dictates of gravity. Yet the outcome would be inescapable, a reminder that cosmic terror does not always announce itself with light or sound. Sometimes it drifts silently, waiting in the dark. But while rogues inspire fear, the more immediate unease lies closer still. We need not look to the distant halo of our galaxy or the intergalactic void to find threats. The nearest black holes to Earth are not tens of thousands of light years away, but a mere handful of thousands, lurking quietly in our neighborhood. Their silence does not make them harmless. In fact, their proximity makes them all the more unsettling. From the wanderers of the cosmos, we now turn to the black holes that dwell close to home, the hidden predators whose presence in our galactic backyard is only now coming to light. The thought of rogue black holes wandering the galaxy unsettles even the most rational minds, for it confronts us with the reality of invisible danger. Unlike stars, which shine as warnings of their presence, or quasars, which blaze across cosmic distances, a rogue black hole is utterly dark. Its only signature is the warping of space around it, the bending of light from whatever lies behind. Astronomers have begun to use this faint distortion, gravitational microlensing, to catch glimpses of these wanderers, but such detections are rare. For every rogue discovered this way, countless others drift unseen, ghosts without trails. If one of these black holes were to pass close to our solar system, the consequences would be profound long before a collision. The delicate balance of planetary orbits would be disrupted, with paths stretched and bent by the newcomer's gravity. Comets from the outer reaches of the Oort cloud could be flung inward, bombarding Earth in showers of icy missiles. Even without a direct approach, the mere passage of such a body within a few light years could send ripples of chaos through our celestial neighborhood. Though the odds are astronomically low on human timescales, the possibility remains, and the silence of these rogues makes them impossible to predict. More disturbing still are the supermassive rogues, colossal black holes ejected from galaxies by the recoil of gravitational wave emissions. Observations have already revealed galaxies whose centers appear strangely empty, as if their hearts had been torn out. A few bright sources of radiation, displaced from galactic cores, may be the first evidence of wandering giants carrying their captured stars with them as faint trailing companions. These intergalactic exiles are reminders that even the greatest structures of the cosmos are not safe from violence. A supermassive rogue would be a city-sized singularity weighing billions of suns, drifting endlessly through the dark void, invisible but unstoppable. The inevitability of their silence makes rogue black holes all the more terrifying. They cannot be avoided, and they cannot be negotiated with. They move according to gravity alone, indifferent to what lies in their path. If they encounter gas clouds, they may briefly awaken, glowing in X-rays as they feed, but most will remain cold and dark forever. They are reminders that the universe is not designed for human safety. It is filled with predators that do not hunt but still destroy, not out of malice, but simply because that is their nature. Yet for all their menace, rogue black holes also whisper of the unknown. Each one is a relic of stellar death or galactic violence, carrying with it a history written in silence. If we could map them, we would hold a record of the life and death of stars, of the mergers and collisions that shaped galaxies. But to map them is almost impossible, and so they remain mysteries, hidden chapters of the cosmic story. With the rogues, terror reaches a new kind of intimacy. They may be far away, but they remind us that the threat of black holes is not confined to distant quasars or exotic collisions. It can come unannounced, drifting across our path in silence. This possibility draws our attention closer to home, to the black holes we already know lie within a few thousand light-years of Earth. Some of them have only just been discovered. Many more must exist unseen. To grasp their presence is to realize that our galactic neighborhood is not as safe as the night sky suggests. From the lonely wanderers of the cosmos, we turn next to the closest threats of all, the hidden predators dwelling near our own solar system. They are silent, yes, but they are close, and in their nearness lies a terror unlike any other. The great terror of black holes often lies in their distance. We can admire quasars from billions of light years away, or marvel at the collisions detected by gravitational waves that occurred long before Earth even formed. But the truth is more unsettling. Some black holes are far closer than we once dared to imagine. They are not confined to distant galaxies or abstract calculations. They are here, in our own galactic neighborhood, hidden among the stars we see each night. The most terrifying black holes may not be the most massive or the most radiant, but the ones quietly lurking just a few thousand light-years away. For decades, astronomers assumed that black holes near Earth would be rare. The first known candidates, such as Cygnus X1, lay thousands of light-years distant, but recent surveys, using instruments with the precision to track subtle stellar wobbles, have revealed something new. There are quiet black holes orbiting ordinary stars, unnoticed until modern measurements uncovered them. These discoveries suggest that nearby space is not empty at all. It is populated with dormant black holes, unseen predators that slumber in silence. The most striking of these discoveries is Gaia BH1, identified in 2022. This object lies only about 1,560 light-years away, practically next door on galactic scales. For comparison, the diameter of the Milky Way is over 100,000 light-years. To find a black hole so near is like discovering a predator lurking at the edge of one's village after assuming the forest was safe. Gaia BH1 is about 10 times the mass of the Sun, paired with a star very much like our own. It emits no X-rays, no flares, no violent signatures. It is silent, detectable only through the tug of its gravity on its companion star. The discovery of Gaia BH1 forces us to rethink our assumptions. If one such black hole exists so close, how many more must be scattered through the galaxy, invisible to us? The answer is likely in the millions. For every black hole that feeds and reveals itself in X-rays, countless others remain dormant, their presence betrayed only by the faintest gravitational clues. We live in a galaxy not of stars alone, but of shadows, each one a remnant of a star that died long ago. These nearby black holes do not need to feed to be dangerous. Their mere presence is unsettling. If a black hole passed within a few light years of our solar system, it could destabilize the orbits of comets in the Oort cloud, sending waves of icy bodies inward toward Earth. A closer approach could tug at planets directly, altering the architecture of our system. The odds of such an encounter are extremely small within human timescales, but across the long history of the galaxy, such interactions are inevitable. The universe plays out its dramas on timescales far beyond human lifespans, and in that vastness, even the rarest threats become certain. The unsettling truth is that most black holes near us remain invisible until we stumble upon them. They do not shine, they do not roar, they simply are. Each new discovery, like Gaia BH1, reminds us that the night sky is not just a map of luminous stars, but also a veil concealing silent predators. To know that the nearest black hole lies only a few dozen generations of human travel away is to realize that cosmic danger is never distant. It is always near, hidden just beyond sight. From the closeness of Gaia BH1 and its kin, the story grows even darker. For as terrifying as nearby black holes may be, the physics that governs them is more unsettling still. The rules that shape their horizons, their singularities, and their interactions with time itself challenge the very foundations of human understanding. If the closest threats unsettle our sense of safety, the exotic hypotheses about what black holes might truly be unsettle our sense of reality itself. The presence of nearby black holes challenges not only our sense of safety, but our grasp of just how incomplete our survey of the galaxy remains. For centuries, astronomy was about the visible, the stars that burned, the nebulae that glowed, the galaxies that shimmered in the dark. Only in the last century did we begin to appreciate the invisible side of the cosmos: dark matter, gravitational waves, and black holes themselves. The discovery of Gaia BH1, lurking so close, shows how much still lies hidden. If a 10 solar mass black hole can rest unnoticed within just over 1,000 light years, then there may be dozens within that same radius. We have not yet mapped them, but their gravitational footprints may already be written in the subtle motions of nearby stars. Dormant black holes like Gaia BH1 are not outliers. They are likely the rule. Every massive star that dies leaves either a neutron star or a black hole. Many of those remnants have companions, but countless others drift silently, undetectable except through the faintest interactions. Future missions, designed to measure stellar motions with even more precision, may reveal hundreds of black holes within a few thousand light years. The neighborhood of the Sun is not as empty as it seems. It is filled with ghosts, dark reminders of ancient stellar deaths. This realization forces us to face the uneasy thought that humanity exists in the shadow of silent monsters. It is not only the distant quasars or colliding binaries that embody cosmic terror, but also the nearby predators we cannot see. Their presence is a reminder of how thin our margin of security truly is. Earth's orbit feels stable, the solar system serene, but this stability depends on the absence of gravitational intrusions. A rogue or even a nearby dormant black hole passing too close would be catastrophic. Such events are rare on human timescales, but they are not impossible. On cosmic timescales, they are inevitable. Yet there is another form of terror in proximity, not of physical danger, but of intellectual unease. These nearby black holes are laboratories waiting to be studied, but they raise questions that even observation cannot easily answer. What happens to the information carried by matter that falls inside? Does the singularity truly crush reality into an infinite point, or does a new realm of physics emerge within? If time itself slows at the horizon, what does that mean for causality, for the very order of the universe? These questions are not abstract puzzles. They are mysteries anchored to real objects, some of which drift only a short distance from our own world. The closest threats are reminders that black holes are not remote or speculative. They are here, within reach, influencing our galaxy directly. They unsettle us not with the spectacle of distant light, but with their silence. They show us that the universe is not only vast, but immediate, that the forces shaping galaxies also lurk in our neighborhood. From these nearby dangers, our journey must now move deeper still, beyond proximity and into the realm of theory, where exotic possibilities push against the edges of science itself. For if nearby black holes disturb our sense of safety, the hypotheses of what they could truly be disturb our sense of reality. We now turn to the most speculative, the most mind-bending, and perhaps the most terrifying possibilities of all: the exotic black hole hypotheses. Black holes already stretch our understanding of reality. They warp space, twist time, and erase the familiar rules of physics at their cores. Yet even these astonishing facts may not capture the full truth. For decades, scientists have explored exotic hypotheses, ideas that push beyond the known into realms where black holes may be stranger than anything we can prove. Some of these possibilities are speculative, born of mathematical exploration. Others are serious contenders, waiting for observational evidence to confirm or deny them. Together, they reveal that the terror of black holes lies not only in their destructive power, but in their capacity to undermine our sense of what the universe truly is. One of the most intriguing ideas is that of primordial black holes. Unlike the stellar remnants and galactic giants we know, primordial black holes would have formed in the earliest moments after the Big Bang. In the chaotic newborn universe, fluctuations in density may have been so extreme that some regions collapsed directly into black holes, ranging from microscopic scales to masses far larger than the Sun. If they exist, they could explain part of the mysterious dark matter that makes up most of the universe's mass. Some might be drifting through galaxies even now, tiny but numerous, shaping cosmic structure invisibly. Their existence would tie together two of the greatest mysteries of physics: black holes and dark matter. Another exotic idea is the possibility of white holes, the hypothetical opposites of black holes. While black holes trap everything, a white hole would expel matter and energy, preventing anything from entering. Mathematically, they appear as mirror solutions to Einstein's equations, but whether they can exist in reality remains unknown. Some theories even suggest that black holes and white holes could be connected through bridges in space-time, wormholes. These cosmic tunnels might allow travel between distant parts of the universe or even across universes, though they would likely be unstable and collapse quickly. Still, the idea that black holes might be gateways rather than dead ends is one of the most haunting possibilities in modern physics. Physicists have also explored the concept of firewall paradoxes. According to relativity, nothing special should happen at the event horizon. An object should pass through without noticing, at least until it nears the singularity. Yet quantum theory suggests that information cannot be destroyed, and this leads to contradictions about what happens at the horizon. Some models propose that instead of a smooth crossing, the horizon may burn with a searing wall of energy, obliterating anything that touches it. If true, then the event horizon is not a silent veil, but a deadly surface, transforming our image of black holes from silent traps to fiery barriers. These exotic hypotheses remind us that black holes are not merely astrophysical objects, but intersections of theory, where relativity and quantum mechanics collide. They are the testing grounds for ideas about the deepest workings of the universe. Whether they hide wormholes, spawn primordial relics, or guard firewalls, they embody the mysteries that remain unsolved. To study them is not only to understand stars and galaxies, but to confront the foundations of space, time, and reality. From these strange possibilities, we step into the final abyss, for beyond the hypotheses and the theories lies the ultimate truth of black holes. They are the universe's most extreme creations, monsters that defy imagination and yet may hold the key to cosmic understanding. To close our journey, we must face them in their totality, as both destroyers and teachers, as threats and as guides to the deepest truths of existence. Exotic black hole ideas reveal how easily the line between science and philosophy can blur. We treat black holes as astrophysical objects, yet they also act as thought experiments that test the limits of our knowledge. Take the holographic principle, for example. This idea suggests that everything falling into a black hole might be encoded on its surface like a projection, with the three-dimensional contents of the black hole described entirely by two-dimensional information at the horizon. If true, then black holes are not just cosmic predators, but cosmic archives, preserving reality in ways that challenge our intuition. The universe itself may function like a vast hologram, with information spread across surfaces rather than stored in volumes. Another speculation touches on time itself. Some models propose that the singularity at a black hole's core may not be the end of space-time, but the beginning of something new. Instead of crushing matter into nothingness, the singularity could act as a bridge to another universe, a seed for a new expansion. In this view, every black hole might be a gateway to another cosmos, and our own universe could even have been born from such an event inside a parent universe. It is a mind-bending possibility that reframes black holes as wombs of creation rather than final graves. There are also ideas about quantum fuzzballs, objects that replace the singularity with tangled webs of strings predicted by string theory. Instead of a smooth horizon, the black hole's boundary might be a chaotic quantum surface where space-time itself dissolves into fundamental threads. This would resolve paradoxes about information loss and singularities, but at the cost of replacing the elegant simplicity of relativity with the strangeness of string theory. If true, then black holes are not voids, but intricate structures woven from the very fabric of reality. Speculative as these hypotheses may be, they remind us that black holes are the sharpest edges of physics. They are the places where equations break down, where knowledge falters, and where mystery asserts itself. They inspire terror because they destroy, but also because they reveal how little we truly know. To imagine primordial relics drifting unseen, white holes spewing matter into the void, or wormholes threading universes together, is to confront a cosmos more bizarre than any fiction. What unites all these ideas is the recognition that black holes are not mere dead ends. They are frontiers. Each exotic hypothesis is an attempt to peer beyond the veil, to glimpse what lies past the event horizon, to understand whether information survives, whether space-time continues, and whether our laws of physics are complete. These questions will not remain unanswered forever. As our instruments sharpen and our theories deepen, we will move closer to truth. But until then, the exotic black hole remains both a symbol of terror and a symbol of wonder. They embody the unknown more completely than any other object in the cosmos. They are not only reminders of destruction, but invitations to discovery. They force us to question what we think we know about time, about reality, even about the universe itself. And in that questioning lies both fear and fascination, both despair and hope. From the realm of speculation, we move now into the final descent, the place where all threads of the story converge. Stellar killers, missing links, galactic hearts, blazing quasars, roaring binaries, wandering rogues, nearby threats, and exotic hypotheses all point to a single truth. Black holes are the ultimate abyss. To conclude, we must confront them as they are, the universe's most terrifying monsters, and perhaps its greatest teachers. From the first whisper of stellar remnants to the unimaginable scale of ultramassive black holes, our journey has spiraled ever deeper into darkness. We have traced the lives of stars as they collapse into killers, followed the missing links of intermediate masses, confronted the galactic hearts that bind billions of stars, and gazed into the blazing fury of quasars. We have listened to the trembling of space-time as binaries merge, imagined the silent menace of rogues adrift, and faced the unsettling nearness of dormant predators in our own galactic neighborhood. We have even wandered through the wild landscapes of theory, where primordial relics and wormhole gateways stretch our imagination beyond physics itself. Now all these threads converge upon a single truth. Black holes are not merely one type of cosmic object among many. They are the ultimate abyss, the final frontier where terror, wonder, and knowledge collide. The terror of black holes is inseparable from their nature. They are the universe's most efficient destroyers, silent engines that consume without mercy and without return. An event horizon is not a surface but a point of no escape, a boundary where light itself bows to gravity. The singularity within is a mystery that mocks our equations, a place where space-time ceases to obey the rules we know. To fall into a black hole is to be erased from the observable universe, to cross a threshold beyond which no message can be sent. This finality is what makes them terrifying. They are not like supernovae or gamma-ray bursts, fleeting explosions that blaze and fade. They are traps that last for billions of years, patient and eternal. And yet, the fascination is equally powerful, for in their extremity, black holes offer insight into the deepest questions of existence. They are laboratories for testing general relativity, crucibles where quantum mechanics must eventually assert itself, puzzles that may hold the key to unifying physics. They are teachers disguised as monsters. In studying them, we learn not only about stars and galaxies, but about the fabric of reality itself. The terror they inspire is balanced by the awe of discovery, the sense that by confronting them, we are peering into truths otherwise hidden from us. Black holes are also storytellers of the cosmos. Stellar mass black holes mark the deaths of massive stars, reminders of cycles of creation and destruction. Intermediate black holes, if they exist, are stepping stones to the giants. Supermassive black holes shape the lives of galaxies, regulating star formation and anchoring cosmic structure. Quasars blaze as beacons from the young universe, lighting our path to understanding cosmic history. Binaries reveal themselves through gravitational waves, letting us listen to the universe's hidden music. Rogues remind us of chaos, of objects flung into eternal wandering. Nearby black holes reveal that terror is not remote but close, hiding among the stars of our own sky. Exotic hypotheses remind us that what we know is still incomplete, that the abyss contains secrets we have only begun to guess. To contemplate all these forms is to realize that black holes are not exceptions. They are central to the story of the universe. They shape galaxies, govern dynamics, and may even play roles in cosmic origins. They are not just destructive, they are essential. Without them, the universe would look profoundly different, perhaps unrecognizable. Their terror is matched only by their necessity. And so, the ultimate abyss is not only a void, but a mirror. When we stare into the idea of a black hole, we confront not just the darkness of the cosmos, but the darkness of our own ignorance. They remind us that the universe is larger, stranger, and more violent than our instincts imagine. They also remind us that our tools, our science, and our imagination are capable of reaching into that darkness and drawing meaning from it. The abyss is not only a place of endings, it is also a place of beginnings, of new knowledge and new wonder. To stand at the edge of such an object, were it possible, would be to feel the pull of eternity. The event horizon stretches like a silent veil, and beyond it lies mystery. Time slows, space curves, and the known dissolves into the unknown. We cannot follow matter across that threshold, but our minds can wander there, asking questions that stretch us beyond ourselves. Black holes are not only terrifying predators, they are invitations to think beyond limits. As our journey closes, the final words are both warning and promise. Black holes are the universe's ultimate predators, silent engines of destruction, and yet perhaps the keys to understanding space, time, and reality itself. To fear them is natural, to study them is necessary, to imagine them is to step into the abyss and return with wonder. Black holes in their many guises leave us with a paradox that no other phenomenon in the universe can match. They are at once the most destructive forces we know and the most illuminating. By their very existence, they erase stars, consume matter, and defy escape. Yet by studying them, we have unlocked new senses with which to perceive the cosmos. Gravitational waves, once a purely theoretical ripple in space-time, are now a tool that allows us to listen to the universe. The shadow of M87 star, captured by the Event Horizon Telescope, gave us the first true image of an event horizon, turning abstract equations into something tangible. Each advance, born from staring into darkness, has deepened our connection to the cosmos. Their terror is amplified by scale. A stellar black hole can consume a star whole, pulling its matter into a maelstrom of X-ray fire. An intermediate black hole, elusive yet possible, may tear clusters apart. A supermassive black hole holds sway over billions of stars, anchoring an entire galaxy with its invisible hand. An ultramassive black hole, like TON 618, stretches imagination to its breaking point, with an event horizon larger than our solar system. And scattered among them may be primordial relics, microscopic black holes formed at the birth of time, each one a reminder that the universe wastes nothing, not even chaos. To contemplate this spectrum is to feel small, to feel exposed, and yet to feel part of a story far larger than ourselves. In their silence lies their greatest menace. Most black holes are invisible, dormant, and undetectable until circumstance reveals them. We now know one of them, Gaia BH1, lies only a little more than 1,000 light-years away. It is quiet, but it is near, and its nearness tells us that our galaxy is seeded with such predators. Some drift in solitude as rogues, exiles cast adrift by violent births. Others lie hidden at galactic centers, their power so immense that they shape star formation and galactic destiny. Whether small or vast, they wait, indifferent to the fates of civilizations or worlds. And yet, to despair before them is to miss their other role. For black holes are not only agents of destruction, they may hold the answers to questions as old as thought itself. What is time? What is space? Is the universe finite or infinite, singular or plural? Black holes touch all these mysteries. At their horizons, relativity reigns. At their cores, quantum uncertainty cries out for explanation. They are the meeting ground of the two greatest theories of physics, and they demand resolution. In them may lie the path to a deeper theory of everything, a framework that unites gravity with the quantum world. In this sense, black holes are not only ends but beginnings, not only voids but gateways. Our journey has been one of awe and dread, of monsters and mysteries. We have seen killers born from dying stars, titans blazing as quasars, and silent rogues adrift in darkness. We have followed gravitational waves across billions of years, and peered into the possibilities of wormholes and white holes. In each chapter, black holes have emerged as the most terrifying and yet the most profound creations of the cosmos. They are reminders of fragility, of power, and of possibility. As we close, the abyss remains. The monsters in the dark still circle, unseen but real, their gravity shaping the stars above us even now. They will outlast our world, our species, perhaps even our universe. And yet, in their silence they speak, inviting us to listen, to learn, and to imagine. Black holes are the ultimate abyss, yes, but they are also the ultimate mirror. They show us the limits of fear, the reach of curiosity, and the boundless scope of the human desire to understand.